appreciate Jim having me. Looked at his work, tried to do my best to follow his footsteps throughout my career. So, we'll be here. So yeah, so I'm going to talk about Siena models. And my goal for today is to really give you an introduction to the model. So. To really give you an introduction to the model, what it can do, why you might want to use the Siena model. One reason might be because you're interested in questions of your influence, you want to control or into it, into relationships. But there are a number of other capabilities within the Siena model. So I want to try to give you some insight into what that range is and some of its flexibility. I'm going to talk about the form of the model a little bit. The real idea is to give you a sense of the intuition behind the model, in the sense that this is an actor-oriented model, or an actor-based model, or an agent-based model. So it's very different from many of the other statistical models we've covered. But if you can wrap your head around what it's doing from this actor-oriented basis, then understanding what the model does, interpreting the model becomes much simpler. So I'm going to spend a lot of time talking about that. I'll talk about the estimation a little bit because that's the actor-oriented nature. Go through an example, and then in a lab that really, you don't have a whole lot of time to get into everything that Siena does, but I do want to show you some of the peculiarities of setting up and running the Siena model. It's different in some unintuitive ways. All right, with that said, what is a stochastic actor-oriented model? Okay, so it's a longitudinal network model. We're talking about complete network data, okay, within some kind of bounded population. That might be a school, an organization, a prison, some kind of bounded population where we've done our best to get ties between everybody in those bounds, or at least people within a certain role, like students in a school. Okay, it wasn't necessarily designed for eco networks. I have seen some applications on eco networks. It's a little bit funky, but it can be done. It's not the best way to answer questions of peer influence, but if a study is designed the right way, there might be a way to do that. So I'm not going to talk about eco networks necessarily, but if folks have questions about that, what that would mean. What we are doing is we're monitoring change across the street once a time. So survey, some data gathered at time 1, another survey at time 2, more data at time 3. So similar to what we were talking about with the Turgo framework yesterday, the exact same data structure we're using. Okay. The plus of the sound is that we can also model change in behaviors. So change in some kind of health outcome, change in some kind of health behavior. We're going to talk about smoking today as our example, but you can think about what work I've done is look at change in weight, change in depression, change in aspects of identity. Really, any individual little thing that changes, we think it changes your influence. You might want to go to a model and test for it. Okay. And I should mention, please ask questions at any time. All right, Jim, you might want to close your eyes for this. This is my one attempt at network, visualizing a network. I generally don't do because I don't know the reason. I'm just not good at it. This is what comes out when I try to model a network. But I think this works in 2 ways. So this is Jefferson, Iowa, at our school. It's a white suburb somewhere in the Midwest. And all this has to do is creating aspects. So this is their network at one point in time. And you don't see a whole lot here. If you look, you can kind of see, so the nodes are shaded by smoking level with darker nodes at higher smoking rate. Some darker nodes over here, some lighter nodes over here. So that's a kind of a hint that there is some homophily. And if we calculate odds ratio, what are the odds of smokers being connected versus smokers being connected to non-smokers, right? We see that we get a 1.5 odd ratio, which is a decent indication that there's some assortativity on smoking. Okay? What we don't really see here, and I don't know if sociogram can show this, maybe Jim knows the way, is the correlation between smoking and injury. Okay? So smokers have slightly more ties coming into them, which could mean smokers are more popular in school. Again, there's nothing to do. So if you're smoking and you've got the booze and the cigarettes, maybe you're more popular. Okay? All right, so look, with the standard model, one thing we can do is try to understand what led to these patterns. Okay, what led to this? And we talked about already, that could be their influence or selection. Right? So here's the problem. Right? We're observing a network on T. We see that, okay, smokers are friends, and we see non-smokers are friends. Okay, well, what led to that? So we often think it's the peer influence, right, where people might have been different initially, but then influence one another such that over time they become more similar. Okay? But the alternative is that maybe there was, they weren't friends, so they were friends with different people, and at the next point in time, we see that they're drawn towards friendships with those who are similar. Okay? So the point is, the same pattern that we observe could be produced through multiple processes. And these are just the two that we focus on. We'll talk about some others later. More generally, this is a pattern of popularity, right? Where we've got the smoker receiving more ties, the smoker more popular. What preceded that? Well, again, it could be that he was already more popular, right? So he took up smoking. Or it could have been that he started smoking, and then that is what led to more and more friends. Okay? So it could have come from either way. So any kind of network behavior association, what we want to take, was this produced through some kind of behavior change? The network set the stage for some individuals to change their behavior? Or was individual behavior already where it was, and that led to certain network selection processes? Okay, you can tear apart most kind of distinguish most patterns that way. All right, so we want to try to discern which routes led to these patterns, because most people are interested in behavior as an outcome. Okay, the standard model can model the network as an outcome and the behavior as an outcome. Most people are interested in behavior, so if you want to understand peer influence within natural settings, we need to think about how people select into those relationships. Okay, so homophily is important. Popularity could be at work. Think about that. Control for that. Okay, so that's selection based upon specific behavior that we are interested in. That's that reverse causality. But we also want to think about selection, influence on things that are associated with behavior. Okay, so it might be that in this school we looked at, the boys are smoking and the girls aren't. Okay, so the boys are all hanging out together. That's what we do. Girls are doing their thing, and so you see this homophily on sex. That brings with it homophily on smoking. Right? It's only boys who are smoking. Okay? Or maybe that smoking is associated with drinking. Right? Drinking leads to smoking. Okay? In which case, if people are associated because they drink, it's not easy to get alcohol in adolescence, so you kind of cluster on the access to alcohol. Then you start smoking together as a product of that. We're always breaking the rules, we might as well. So it might be something about alcohol use in smoking. So you can imagine the pathways get pretty complex. We've got multiple kinds of things that might be happening. Selection on multiple behaviors, influence on multiple behaviors influencing one another. So we want to try to wrap our head around all of those. It's also possible that network processes can amplify the level of homophily, right? So The example here, let's say A really wants to have friends who are like him, okay? And so A only befriends people who are like him. So A is a non-smoker. A can't stand smoking. I'm only going to be friends with people who don't smoke. Okay? Over time, A's friendship with B becomes reciprocated, right? Because that's what we do. So this now B thinks that A is a friend. Sorry, goes to the back. You can't see. But B becomes A's friend. That tie is driven by reciprocity. B may not care about smoking, not smoking, right? Kind of different. But we now have a tie that is between non-smokers, but it's not driven by similarity. Similarly, over here, if B and B form a tie, it's a tie between two non-smokers. It looks like a monopoly, but it might be driven through transitivity, just because we've got a friend in common. Okay, so again, we want to think about these other processes that are at work and driving friendship and can create the patterns that we're interested in that aren't the source of those patterns. Right? So simply seeing monopoly doesn't mean it's a preference for monopoly. Try to emphasize my work. Okay. All right. So when we want to use this now, okay, questions about how networks affect individual behavior, like peer influence, diffusion, things like that. We also might want to think about it if we're simply interested in network change. Okay? We're not interested in any kind of behavior. We just want to model how a network evolves over time. Maybe it's testing out different processes that can lead to homophilies. I've done some work looking at whether kids who are at risk for depression are more likely to kind of withdraw from social interaction or if they're excluded from others, kind of excluded by peers as a result of that depression. More generally, questions about how do we acquire the networks, how do we acquire those peers who influence us. I think that if we really believe that peer influence is operating, we need to look at the other side and figure out why do people have the network positions and the network structures that they have. We can use the sound for that. So basically, Scott talked about targets yesterday. Most questions that you would want to address with a target, you could address with a CNN model. Some differences in assumptions, but in general, if you're thinking about network change and you've got discrete panel data, you can use a CNN model. Okay? You might also be interested in questions about how do networks and behavior change and how does that accumulate into macro levels, prevalence levels, or thinking about questions like cumulative disadvantage, right? So if we have behaviors clustered within groups, and you might see those groups converging over time, or polarizing over time. So we can use the Siena model to model these processes, and then some of the simulation capacities for other kind of decomposition methods to try to understand which of these micro-level patterns is responsible or shares more responsibility for any macro-level patterns. Okay. One of the kind of overwhelming things about a Siena model is that you can have multiple outcomes. There's always at least one network outcome, but you can have a second network, third network, you model multiple networks evolving over time and influencing one another. We're going to be talking about friendship, but if you had a network of status between peers, a network of who studies together, a network of who shares needles together, right? I don't think that is happening in Jefferson, but you put all of these, and it would be a mathematical model. You could look at these multiple networks. You can bring in multiple behaviors, smoking, drinking, mental health. You can bring in two motive networks. So people at different kinds of contexts, different kinds of full stuff. So students in different activities, students in classes, students in different informal spaces where they hang out. You can model all of those over time and their interrelations. Okay. So, and thinking about kind of different models and things we talked about this week, you can think about the network models on two levels, right? It's using the network to explain some individual behavior, in which case you've got a series of models you might want to use, varying complexity and how much of the network structure you want to try to account for. Okay? In a linear model, we may not be accounting for anything, right? But we get up here to some of these other models we're accounting for interdependence between people in the network. We also have models where the network is the outcome. Okay? We talked about some of these, QUAT model, Ergom model, where the network is the outcome, and individuals are more or less stable across time. All right, so the SINA model, the Brown brings those in and models both at the same time, and allows them to shape one another. There's a merging model. Just came paper on it just this year. There's a cross-sectional model that gets at selection. I'm not sure how that works. I've wrapped my head around it yet, but it's basically it's built on the Ergom framework. So if you're really interested in these questions, stay tuned to see how people use. Yeah.
Question. Can you help me understand why a network would be the outcome, or if it's a boundary network already? Can you explain that more?
So the relationships are the outcome.
I see.
Yeah.
I know you mentioned earlier on that this is not ego networks, but I was just wondering, maybe it's not peer influence, but something like in like a health discussion network changing behavior, something like that. Is it possible to model in an ego network and similarly to track influence?
It could be, yeah. The challenge with ego networks is you don't have the opportunity for possible relationships. So the trick to make that work is what we talked about. You have those alter ties, which maybe they're there, maybe they're not. And you can treat alter ties as the ties of interest. The other challenge is modeling kind of change. You need good behavior on those alters and their change over time. And if that's coming through ego, how well can ego report that, right? It's like self-attribution bias. It's challenging, but I've seen it done in terms of modeling change in structure. I think that there's something there. It would be hard to read those. But maybe you could do it. That's a challenge. Okay. So yeah. So because the SINA model, the Ergom use quite similar things on the network side. I just want to touch briefly on what we're doing that's different. Okay. So the Ergom and the Stergom talked about yesterday. So here we're taking a model at one point in time and then modeling discrete change for the next point in time. Okay, so we're modeling the ties themselves. Okay, which ties have changed, which ties are the same. It's very much a regression of one time point on the previous. The Zaum is a very different mindset. Okay, the Zaum is this action-oriented model where we're taking the observed network at time one. We're going to start here, and then we're going to put this agent-based model on top of it, where we pick actors and allow them one by one to change one time. Okay, and we're going to put some effects in our model to determine how actors choose which type of change. Okay, but we're going to go through this one by one. And eventually, if our model fits well, then over a long series of these changes, we get a network at time two that looks a lot like the network we observed. Okay. This is a way of implementing an MCMC algorithm. It's taking it down and implementing it from the actor's perspective. So let me just show you how this here we have a visualization, over to the Adams, of what is the Siena model doing when you're just staring at a screen happening in the background. If you can see here, there's one node that's red. This node has been randomly selected to consider changing their network. Okay? So keep an eye on this. Let's see what happens. Okay, at a time. The network shifts. The algorithm then moves and randomly selects another actor. Right here. Okay? We're going to let that actor consider all possible ties. What effects are the model here? They're considering all ties, and they're going to make that change that maximizes their utility. Talk about what that means. They don't do anything. They're happy where they are. All right, and now we've got another node up there at the top that's primed to consider changes. They dropped a tie. This is like, where's Volvo? Right down here somewhere. There it is. Here. Okay. What are they going to do? They dropped a tie. Okay. Now we're down here on the very bottom. That person did nothing. Okay. You can run through it, right? Track how the network changes over time. And this is part of building that intuition. How is the Siena model assuming change occurs? Okay, it's really step by step by step thing. Happens much faster, thankfully. Not fast enough still. But, all right, so that's the idea. Well, yeah, go.
So what happens when you have larger chunks of the network detaching from the broader network, and then that network is going to change the configuration.
Okay. Yeah, so I'll talk about that in a moment with ways to think about whether some actors are changed more rapidly. Let's make that when we get to rate functions. And talk more about the model itself. Okay, so it's a stochastic actor-oriented model. Before that, it was a stochastic actor-based model. Before that, it was a Siena model. So you're going to hear all these different names. Siena actually stands for Simulation Investigation for Empirical Network Analysis, which is a way that Tom Snyders, I think, really was fascinated by Siena, the town of Siena in Italy, and wanted to name his model after that. I think he did present it there first, presenting it to an academic audience. But it's affectionately known as the Siena model. But when we write about it, we use this more technical language. It's in our Siena shortly. And again, it does this nice thing of estimating network behavior change and more than that. All right, so how does this work? Okay, well, we've got two discrete ways of data, at least, that we're looking at. We're assuming continuous time between those two ways. We're assuming all these microsteps, thousands of microsteps between these, and we're going to model what happens across these microsteps. So we're going to imagine what could happen. We're actually going to engage in kind of a hypothetical exercise, wherein between these waves we say, what if actors follow these rules? And then we see if actors following those hypothetical rules produce a network we observe in line 2. Okay, so it's really an agent-based model at the heart of it. What the assumptions is that actors control their outgoing ties. So I control who I say is my friend, or who I say I get advice from, or actors also control behavior. So this kind of data or model really wouldn't be appropriate for. Well, there's a variation that does allow for some bilateral kinds of model itself is specified as two functions, two for network change, two for behavior change. So when we're talking about modeling change in the network, we've got a function that determines when new changes occur, how often new actors have an opportunity to change their ties, and then when an actor has a chance, what tie they choose. Okay? We tend to focus mostly on this question, two people choose, and tend to assume that this is uniform, right? Everybody's got equal opportunities to change. But if there's something that people move into a new context, or something the question came up earlier, you can adjust this. The rate function gives some actors more chances to change. Actors with some attributes might have more chances to change. You might imagine in a school, freshmen entering the school are changing their networks more rapidly than older students. So that's something that you put in there for that. Similarly, on the behavior change side, we've got a function that how often do actors change their behavior, and then when an actor is chosen to change their behavior, what behavior do they choose? What level of behavior do they choose? Okay. So the objective function looks like this. I don't want to, I'm not going to get too much into this, but I do want to point out though, it is, it does have this linear form where you've got a series of effects, beta, a series of, or coefficients beta, a series of network effects, SKI, or different network configurations, things like reciprocity, sensitivity, or homophily, that are applied to the network in its current state, inform these actors' decisions. Okay, so what during model building we're doing kind of the same thing we always do. We're trying to come up with a set of coefficients. All right, so what does that look like? Because this is where it starts to really get somewhat different from other methods. So again, we're taking an actor-oriented perspective here. Okay, so during estimation, actors are randomly chosen, change their ties. Let's say we've got a model set up like this. It's got an out degree parameter, like an edges term, an Urban model. Okay, and it's an effect that gets at how many ties do I have. Right? If I add a tie, how many ties do I have? We're going to say it's at a negative 2. Coefficient, assume that's the case. Reciprocity is this, if I send you a tie, you send me a tie, right? That's got a positive coefficient. So let's say this is our hypothetical model. We're going to test this, whether these parameters work. And so let's say in our network here, Ego is chosen to change their ties. Ego is going to go through every possible tie, every alter, and consider what is the value of changing that tie. Okay, Ego has a tie to J1. What would happen if Ego changed that tie? So if Ego dropped that tie to J1, that would reduce Ego's numbers of ties to 1, which gives us a negative 2 from this part of the equation. That would be dropping a reciprocated tie, so Ego would have no reciprocated ties, so that would give us 0 here. Works out to be a utility of negative 2. Okay. Ego could also not change any ties, drop a tie to J2, add these other ties. For each of these, we're going to say, well, what would that, how would that affect these different statistics in the model? And you follow the math there, I'll let you do that on your own. But it works out to be each tie, potential tie, or dropping a tie, has a different utility according to the current model. According to the current set of coefficients here. Okay, and so based on where we are now, dropping the tie to J2, which is adding a tie, adding ties are costly, adding ties are costly, so dropping that tie is good, especially because it's not providing any benefit. It's not a reciprocated tie, which actors value. So Ego's likely to drop that tie. we do, as you mentioned, we add a little bit of error. The model has a little bit of error to make this stochastic. But right, so in case of pi, there's some error and there. All right, so Ego drops that pi, and then the model would select another actor who would evaluate the current network, right, which is pi from Q to the J2 drop, and evaluate all possible pi's. So make their own decision. As you can imagine, over time, Ego might drop the pi to J2 now. Ego might add it later. Right, you can see ties coming and going between. This is a simulated sequence of changes between two operations. So there might be all kinds of changes occurring and recurring over time. Okay, so what kind of effects do we include in the model? These are just some of the most common ones. Alpha degree to control for pi velocity. Think of alpha degree as an intercept in the model. Keep the probability of the pi constant, or at least not necessarily constant, but to not have networks that explode with ties, have too few ties. You want to keep that probability in line with what we observe. Network processes like reciprocity and transitivity. You can also think about attribute-based effects. So we talk about homophily, but also sociality. Actors with certain attributes might send more ties. Actors with certain attributes, right, might receive more ties. Okay? These things can be stable or time-changing. That's okay. Oftentimes, dyadic attributes are really important to control for. Right? Things that bring people together. Right? The students being in the same classes, or being in the same clubs. Right? These are really important for understanding how networks work. All right. So that's the network side of the model, and so what we're trying to do with the model, again, it might sound like we're just making stuff up, right? We're just simulating changes over time. What we're trying to do in fitting a model is we've got it at two discrete time points, starting at time 1, and we're simulating. Okay? We've got this time 2 network that has certain properties. Right? It's got a certain number of ties, a certain level of reciprocity, a certain number of triangles, a certain amount of homophily, right? So all these patterns in it. The model is trying to fit those patterns. So we've got a model that we just talked about, a model with alpha degree of reciprocity in it. We're trying to take the network observed in time 2. What's the rate of reciprocity? How many ties there are? Let's try to recreate it. Find a model that will recreate that. Find a set of coefficients for alpha degree of reciprocity that when we apply this simulation, those estimates, you get a network that looks like the observed time 2 network. Okay, so we're not fitting the actual ties, which ties actually exist at time 2. That would be really, really hard. Instead, we're trying to have a model that can recreate networks that have the same properties as that. And when it comes to behavior, we've got a behavior function there. We're testing for peer influence. We're trying to do the same thing. We're trying to come up with model estimates that when actors follow those rules, we get a behavior distribution that looks like that observed distribution. So the level of smoking is the same. Distribution of across individuals, right? That looks the same. Okay. Okay, so how do we do that with the behavior? Behavior function is in some ways simpler. It's like a multinomial logistic model. One of the unique things about SAM models is they're designed where kind of network behaviors themselves are these discrete values. Okay, so take whatever behavior variable you're used to working with. It smoking you saw earlier was 0, 1, and 2. You've got something like BMI, it's a nice continuous measure, you've got to turn it into these ordinal categories. Okay? There is a scanner model, or a version of the model that was recently developed for continuous outcomes. There's not as much work done on that yet. So most of the model you'll see looks like these kind of ordinal dependent variables. You lose some information there, and you're really just trying to capture major changes. Going from not smoking to smoking, big qualitative change. Okay, so we have a behavior function. It's similar in some ways. It takes a set of coefficients, takes a set of effects here. Notice that these also include the network X, right? So the network can inform smoking, and the estimation algorithm, this simulation algorithm looks a lot the same. In the sense that we're going to randomly kind of identify an actor, give them the chance to change their behavior. Randomly identified actor can increase their behavior by 1 step. They can decrease their behavior by 1 step, or they can stay the same. Okay, so that for any actor, it's those are the 3 choices of what they can do. And they'll do a similar thing where consider each possible change, what is its utility based upon the current model, and then make that change that maximizes the utility. And so a behavior function, I think it's helpful really to think about this. It's different from a regression, but the regression framework doesn't break down a whole lot in terms of thinking about effects. So if you were going to predict smoking, well, here we have a linear and quadratic term, which is kind of like an intercept in our model, and it maintains the overall distribution of smoking. Smoking tends to have this U-shaped distribution, where you've got non-smokers, and you've got smokers, and not a whole lot of people in the middle. Okay, so you have a function of effects to control that distribution. We've got an effect of peer influence. Right? So what is people who are currently my friends, what's their smoking? We can look across peers and get the average of those peers. How does that influence my level? We can also look across peers and say, well, do I have any peers who smoke? What's the maximum number? Or do I have any non-smoking peers or friends? Pick a different way to do that. And then we can include a number of controls. So we would do typical linear model things we want to control for. That can include other aspects of the individual's position. So we can include something like immigrant. How many people name me as a friend? Put that in there, or other kinds of network. Maybe close friends, we could be within dense friendship groups, segment that on our own. Put that in there. So you can have a number of different kinds of network effects. So a model might look something like this. We've got a linear effect, a quadratic effect to control the distribution. We're going for stage here, and then we've got one version of similarity. This version is how similar here, weighted by the total number of friends. So with this model specification, we can go through the same exercise where we identify a hypothetical, identify one of the actors in the network, and give them this choice. What do you want to do? Okay, well, if we choose somebody who's at level 1, they're at level 1, they could stay at level 1, they could drop the no smoking at all, or they could go up to be a more frequent smoker. And when this actor evaluates that, we're evaluating the potential new behavior. Right? So we're evaluating a 0, a 1, or a 2. So we plug that into our linear equation, our quadratic equation, plug it in for our multiplied by our age effect, and then we've got to figure out what that means for total similarity. I'm not going to walk through all of this. But this is the equation we're using. And it works out to be a little bit differently for each actor depending on their level. Well, similarity in each of these has a different level. Right? So ego's got a tie to J1. They're both smokers. And this function gives 0.95 in this evaluator. Same as this function here. These two different levels of smoking when there's no tie and not changing at all. There's no tie from ego to this. So those peers are not friends. You do not name them as friends, so they don't. Their behavior doesn't affect ego at all. Okay. So this is how similarity changes. If ego stays at level 1 of smoking, if ego were to consider dropping their smoking level to 0, then we calculate, well, what does that mean for the similarity in each of these dyads? Well, these drop down, and ego's friends becomes less similar, and so that drops down. These other two still aren't friends, right? So it should be nothing. So the overall similarity drops down to 0.9. Likewise, if ego increases the behavior to 2, we see that again, ego becomes dissimilar to J1 and J2. So that similarity is lower. So ultimately, we see that the similarity is greatest for staying at level 1, similarity decrease in these two. So when we add all of this up together, the highest utility looks to be becoming a heavier smoker. Right? And that's driven by the quadratic shape effect plus the age effect. The age effect is driving this. So we see that actually, even though peer influence is a positive value in this network, ego is making a decision that makes them a little bit more different from their friends. Okay. Any questions right now, or have I totally confused you?
I have a question for you with the assumptions behind utility calculation. How much do you think that there is a basic assumption of the knowledge that each agent has of the other?
Yeah, I mean, we're really, so that is my assumption. Right? Actors are considering every possible, here in a network to be a friend, or every possible value of a behavior. That's probably less problematic. It's really, do you know that behavior is an option? And evaluate that. But assuming that kids in a large school know everybody else and know their attributes and their behaviors, we're likely pushing that too far. So something like things that are visible attributes, maybe it's okay. The things that you don't see, if kids aren't smoking at school, where does that information come from? So that one, I think that, it would be, I don't think the patients are violating this. We're always pushing that one. Now, a lot of folks are looking at smaller schools, stuff. Small schools, small settings, classrooms, right? You do have a landscape, right? You can see the landscape and you kind of know who your friends are. The assumptions are a little bit more easier to meet there.
Is there any kind of study incorporated into sample of an amount of error in the depending on
One thing that has been done, Tom's been working on a model that tries tries to differentiate ties within a closer social distance and give those greater allows kind of greater weight to ties at a further social distance. Try to get at asymmetry and information that goes along with social distance because kind of test the idea that well most of the ties that we have are within a close close social distance. Friends are just part of the same social circles, or generally, not maybe one way to try to get. So there's something really hard about that. Yeah.
So all of these models then assume a fixed landscape, so like the landscape itself is dynamic. And you also then model that these actors, or you have both of them at the same time.
So when you say landscape, do you mean the set of actors there, or something?
So like the physical, so like these examples have been like abound in schools. So like the school, the composition within the school is changing. The structure itself is not changing. So what happens like when groups of people are moving to different places?
Yeah. Okay. Great. Yeah. So that's fascinating when that happens. So you can imagine middle schools merging into a high school, or class assignments change from year to year. So we can handle if we have that information. So that would be exogenous. We sometimes exogenously change covariates. Those examples would be you could imagine having a parameter in the model that's are we in the same school, and that changes over time. We're in middle school. We're in the same school, but people in the other middle school are not. But then we're all in the same school. We could also imagine modeling that as endogenously. So, for example, we're looking at extracurricular activities, and those change from year to year. Activities kids are in. So we could have a two-mode network that is kids, which activities kids choose, and then being in the same activities is a predictor of friendship. And that, but that's endogenous in the sense that being friends can also lead to choosing the same activities. So you can do it that way. We only not a catch, but things need to be measured at the same time. So if change in the network is occurring different rates than change in the landscape, we want to try to find out a way to time those. So it's challenging with activities. They change kind of semester to semester, or weird sports having great seasons, but don't necessarily change when we're measuring our network. That's something that definitely yeah.
But something like COVID, some big, large scale event was not outside of the network, but affects everyone in the network. Is that like is that a network effect, or how do you account for something like that, which might have a significant impact on everyone in the network? Where do you put that into this model? How does that fit into a general function?
Yeah. So what I would do is ideally we have enough waves of data that some are prior to COVID and some are after. And we could put a covariate in there for time and test whether something is different during that period of we're all remote and is the effect of being in the same classes goes away. It's really weak for that point in time. So we can have time. So the model by default will assume that effects are constant. Reciprocity is having the same tone status is constant throughout, but we can and should be checking for whether or not there's heterogeneity. And at some points in time, some of these processes are more common. So in some other work I've done, we see that when people enter a new setting, one of the strongest effects is gravitate towards people who are similar and visible characteristics. Right? It's about just kind of finding your place. And then over time, other processes become more important. So you begin to meet friends of friends, become similar on other kind of hidden attributes, things like values and beliefs that are more important than just surface attributes. And so you can imagine doing changes that either changes at the individual level, changes at the international level. You can capture that again if you have the data. The data is so hard to get. You want lots of ways. Ideally, you want lots of ways. You need at least two. Three is a lot better because that's twice as many instances of change as only 2 ways. Three is great. More is better, but you can get the same boost. Yeah. So this came up yesterday, right? What size networks do we need? We need networks probably the smallest. I would say is something around 30. If you have enough waves of data, you can model change. If you only have a couple waves of data, you want to bigger, larger networks. Try to have the same amount of the dyadic level change. Yeah.
Is there a upper limit of what might be feasible if your model changes after
So I've seen analysis up to about 2,000, and you can do more. You're pushing on this assumption of full knowledge of the network. So another thing you can do is look at multiple networks. You can use a multi-level study. So you can take a multiple classrooms within a school, model each classroom evolving separately, and then combine those. And that can get much, much larger than that. But that size is good for one bounded network. I want to be cognizant of time because we are going to jump into R. So let's get a lot of this. All right, so let me talk about how we interpret this. This is something where I see it a little bit different. So we get some results from a model. On the network side, it's useful to think about this as a logistic regression. Like Scott was talking about yesterday. Think of it as a logistic regression, where the unit analysis is the dyad, but instead of it being the probability of odds of a tie, it's probability for log odds of an actor making a tie, selecting an alter within one of those change opportunities, within one of those small change opportunities. Okay, so the outcome is a tie. It could be forming a new tie, but it can also be keeping a tie that already exists. The model, the default model lumps those together. Okay, so when you see a positive coefficient for, let's say, it's the same smoking status, that means that people are likely to add smokers as friends or keep smokers as friends. Someone who's similar smoking status to themselves. Okay, so it's that maintenance or forming a new one. There's also a temptation, like with this regression, to turn these into from log odds into odds, and that can be helpful. The caveat there is that that's assuming that everything, that interpretation assumes everything else is equal, right? It's all fixed at some level, and you're just changing how this going from being the same unsmoking to being different unsmoking, change odds by holding everything else. Right, well, that might be a really big kind of problematic sometimes because the networks will oftentimes have effects that are interdependent. Right? So if you have a model that has muscle and smoking, but it also has a popularity on smoking effect there, that means that both of those effects change or are impacted or come into play if I change my smoking status or a partner changes their smoking status in that hypothetical scenario. So you want to sometimes have to look across multiple effects to understand the implication of differences. All right, when it comes to the behavior function, so this is interpreted effects is how does a one level change, when you get change in our predictor, affect the log odds of being at a certain level of behavior versus one level higher. That could be, so the effect doesn't necessarily mean someone's increasing their behavior. So specifically with a positive coefficient doesn't necessarily mean that having this thing makes people's behavior increase. So a positive peer influence coefficient, like look at that and say, oh wow, peer influence is positive, so people are increasing their behavior in response to their friends. Well, that's one possibility. But it could also be the case that if my peers aren't smoking, peer influence might lead me to not smoke. Right? So it might lead to a decrease in my behavior. Okay, so I want to push you to think that these coefficients do not necessarily, remember these coefficients do not necessarily, you're not predicting the level of the behavior or time, direction of change in the behavior. It's different from models of change in that regard. Instead, you're predicting how this, or calculating how this affects the level of the behavior that's most attractive. So, all right, so I've got a number of examples in here. I don't think I want to go through all of these. I hope it's detailed enough that you can go through it on your own and try to understand what each of these effects are getting at. But this is a typical Siena model, right? This is a behavior for a network function. What's that, about 25 effects? And that's probably an average size. We're interested in this example, smoking. So we've got some effects for smoking in here, but we're controlling for a bunch of other things that people select eyes on. So network stuff, doing the same activities, gender, age, delinquency, alcohol use, and grade point average. Okay, so we can go through a lot of these. One that I do want to show you is this smoking, right? The smoking status. We've got a positive effect for homophily, a positive effect for smoking ulcer, implying that homophily is present, but ulcers are also popularity. To really understand how smoking affects friendship, we've got to interpret these combinations. Okay? So that's what we're doing down here. Is we're calculating for different combinations of people also smoking, what are the odds of high? How does that part of the objective function I showed you earlier, as we work through all of that, well, we can just pull out the two smoking effects and look at what does it mean? How does an actor who's a non-smoker and these potential alters ignoring the rest of the things, what does that contribute to that function? We see homophily, non-smokers choosing non-smokers, a little bit stronger homophily, smokers choosing smokers, a little bit stronger tendency for those relationships to form and persist. And then a really strong aversion here where smokers are not befriending non-smokers, non-smokers also not befriending smokers, but not necessarily as strong. I actually expect that to be the other way around. But again, this is Jefferson High.
What's the scale of those numbers?
This is a contribution to the behavior function, so and that's a log odds.
Log odds.
Yeah. It's basic idea is you compare these different scenarios, right? Which scenarios are more or less likely. Okay. Here's what a behavior function would look like. We've got our distribution effects ahead earlier. These are all effects of different attributes, and then our average similarity stands out being the strongest, almost fully effective. So you can walk through and look at what these mean. This is the U-shape smoking that I mentioned earlier, and how that's calculated. Here is how we think about average similarity. Average similarity, it turns out to be something that ranges from 0 to 1, where 0 is the most dissimilar, 1 is absolutely similar. So we're looking at how, we're talking about how average similarity, in effect here we're going from all my friends, a 1 unit change means all my friends are maximally dissimilar to all my friends are as similar as possible. How does that affect my behavior? And you see that that has a pretty effect, right? That's what you need to do. Exponentiate that to get the effect. We really like the effect. All right. I do want to mention that we do get this effect the same way that we do for ergoms, right? We do these, calculate how the model is able to reproduce statistics from the observed network. With behavior, right? We can look at the distribution, and how much that distribution, but also some other, we can think of other more developed measures. All right. Last thing before the lab, I want to just mention, there are some resources out there, and I really would encourage checking out good overview article. It's still good, even older. Really captures the model. But Tom Snyder's has a website with an immense amount of information. A manual, probably 200 pages now, that really is essential if you're going to be modeling, because it helps explain the kinds of effects, how the model works, the kinds of data you need. It really is one of the most detailed models that the manuals I've seen. But also, he mentions workshops, because if you're going to be doing this, I know a few people who pick this up on their own, and I'm very impressed. But there's some week-long workshops here in Europe that are incredibly useful. Okay. I need to jump into this lab, or we're never going to get there. So while I'm shifting over, does anybody have questions? Yeah.
So I don't know if I missed this, but when you're dealing with the behavior function, right? Like going through this, it seems like the assumption is like when you look at things like smoking and sex, right? Like it's treated very continuously as a node property, right? The level of activity, and like the way you can transition from smoking to non-smoking is kind of parallel. But like you can imagine, like with smoking, for instance, like there's an addiction risk. So like once you start smoking a certain amount, it's harder to transition back. Similarly, like when it comes to like tie formation processes, it's not so much like level of sexual activity, but some sort of like concept of virginity and stigma, something like that, right? It's the idea, like I'm thinking like SI versus SIR and like an when we're thinking about epidemiology, like how does that sort of different trajectories of like changing state happen in behavior functions?
Yeah. So I wish I had 3 hours, because that's the back end of the slides.
Okay.
A little bit. So we can. So I should mention. So for the network, we can separate out adding a tie, and have a set of effects for that, parameters for that, and maintaining versus dropping tie. Those will be separate models. So a lot like Sturgeon, you can have separate models for those two. You can do the same thing on the behavior side. You have one set for increases, one set of effects Yeah, we did that with smoking, trying to get at that, and your intuition's right on. We found that there's strong influence right here, like you see, when you specify a separate effect with an offset, but if we're considering, I'm considering decreasing my smoking, what is the effect of decrease with that decision? They don't matter at all. Their influence goes away. It's all in that direction. So what it's really doing is it's taking that behavior function. You can really think of it as two behavior functions that are constrained to equal, one for increases and one for decreases. And default is keep those equal, free up parameters. So yeah, having fun work. Yeah, so that's one area where the SIEM model is different from the Sturgeon. The Sturgeon requires that you specify what is my model for formation, what is my model for solution. The SIEM model keeps everything constrained to equal. You have to come in and decide if you want to do that. All right, so I think you've got the script open. Get it going here. This is, so we'll work with the smaller set of data that comes with the CM package. These are 50 Scottish girls who are learning about smoking and drinking. And so they're learning from each other. I spoiled the okay, so what I'm going to show you kind of how the data are structured, and some of the steps to get that manipulated into something that's standard use. So alcohol use is in this thing called S50A. It's a data frame. So if I'm looking hard, you probably have a studio. See the data better than I can. But if you look at the first 10 rows, right, you see 3 columns. Alcohol use time 1, time 2, time 3. It's this nice ordinal thing here. Looks like it goes from 1 to 5. Documentation tells you what those are. 5 is the highest level of use. And if you look at this is the frequency distribution across waves, right? You see that there tends to be some increase in alcohol use across time. Okay. You look to see how much change in there is there. So you see that about 50% of girls change from time 1 to time 2. So there's some change here. Not so much change, right? We need some stability there as well. All right, so we've got alcohol use. That data structure is probably up where you're used to. We've also got networks here. So those are S5051, which is time 1 network. It's a matrix. You see here it's 50 by 50 social matrix. I'm going to put these into a list. That'll make some things easier later on. If you look at this, the one thing is, we need to have the same set of actors every time. And even if some kids come and go, we can account for that in different ways. But it has to be the same dimensions across each time. Okay, so we've got 50 each one, and for our network, it's square matrix. If we're doing a 2-mode network, people choosing activities or something else, that's okay. It would be square, but we would do something different. Okay, we've got 113 times, a few more across our 2 time points, and no missing values. That's important to know. Sienna won't blow up with missing values. It does have some indication along the way. So you can still estimate the models with some missing values. cause trouble. So we want to make sure that we have enough stability, right? Balance, stability, and change. So the card coefficient is a good measure. It's the proportion of ties that are stable between two, proportion of ties that are the same between two observations out of all ties that are present across the two observations. And so you see here, that is 0.33. So a third of ties that are ever observed are observed at both time 1 and time 2. If you look at time 2 and time 3, you see 38% of ties are observed. And that's good. So for a Siena model, we want at least 0.2. If they're small networks, the larger the better. So that enough information kind of anchor things. So I'm going to stack these into an array. So we stack these three networks into a three-dimensional array. That's going to make it easier to look into Siena. So you see we've got a 50 by 3. Okay, use colors later. Let's take a look at these. Okay, so drinking on top, smoking on the bottom, but really not going to talk a whole lot about that. You can kind of see the darker colors mean higher levels of drinking. So you do kind of see some, it looks like maybe well, you see change. I'm scared to see it's confusing. I think if you scroll on that, you can see that.
What's the time difference between the two rates?
Good question.
Almost in one academic year.
Was it one academic year, so 6 months or so between rates?
So it's like September to July or something like that.
Yeah. All right. So now, this is what we're really getting to here. How do we set this up for Siena? Because Siena's it's weird this way, to be honest. And there's two ways it's really weird. One is to set up the data. You have to create what's called a Siena data object that contains all the data you want to use for a model. So bring it all into one object before you do anything else. And you have to, as part of that, tell Siena what role each piece of data is going to have. Right? So what is my network? This is my network. What data object is my network? Any attributes I want to bring in, let's bring those in and tell Siena that this is a behavior that's going to be modeled endogenously. This is an exogenous behavior that can change over time. Right? This is an exogenous behavior that's not going to change over time, like gender or sex. This is a network that's exogenous, right? Like what classes students are in. It's exogenous, but it's going to change. Right? We have to tell Siena each of these things, specify all of those up front. And so I actually, there is a slide in here. Slide 64 tries to summarize what those are and the script you would use to specify that kind of object. Okay? So we have to specify all of these things up front. So a friendship network is a Siena dependent variable, and we're putting in this set of networks across 3 time points. Let's see. Okay. So drinking and smoking, you can make those dependent behaviors. Okay. Meaning they're going to be in the model as an outcome. This family event is a time-changing covariate. Household composition change. A constant covariate, we're going to use drug use at time 1. It's simply a static, not changing. So we're running all of these, and then we're going to combine them into this Sienna data object. Sienna data create. Put everything in there. All of the variables that we want to use somehow, or the data objects we want to use as variables. We'll create this thing, and then Sienna tells us, all right, this is what you've done. You've got 50 actors. You've got one dependent variable called friends, so one node network. 3 time points. You've got drinking as an outcome. Short summary of what we've got. Now, you can also set up our data a lot of other ways. Just the network as an attribute. You could bring in smoking as another outcome. The one thing I want to mention, anything you put in here as an outcome or as a dependent variable, whether it's behavior like smoking or drinking or whatever, or it's a network that you're modeling, the model is going to include that. It's going to try to model that change. You can't set it to 0 after this one. So whereas we might want to put in every variable we might ever want to imagine modeling, that's okay for things that are going to be independent variables, but not anything that's going to change in time. So I might, in the back of my mind, I want to put smoking in here because I want to model it, but I want to understand alcohol first. So let me do a bunch of modeling with just alcohol, the network changing, and then we'll get to smoking later versus trying to do all of that once. Okay. So a good idea, so this is more involved report, a set of descriptive outputs that this data will create. That's a little bit more descriptive than this, also has some information on the ranges, missing data, hard indices, some statistics that, or summaries that get used. Let me just show you here. We go to whatever your, so this will save it to whatever your working directory is. Output, here, the text file. Right, it gives some of the same summary. So this is the data object you just created. The data object would be the basis of your model. So this is what Sienna thinks you're working with here. So it's a good idea to check. It gives some degree distributions, numbers of missing data, missing values, means, right? So you can go in and make sure you put the right variable in there. Right? You've got multiple variables, right? And you go along the way. Did you get the right one? Did you get the one that treated missing data the right way? So we also have some information here about how much change there is. This is what I want to point out. For some statistics, Sienna will center every variable if you let it. Right? Being centers everything. In general, helps with the estimation. It does this without you even asking for it. So you got to know it centers everything. That means when you're interpreting effects, you have to take that centering into account. I'm not that effective. So it centers based upon an individual attribute. It centers based upon the mean across individuals. For dyadic attributes, like same smoking or similarity in smoking, it centers across dyads, which isn't so easy to calculate. Right? You for that, push the button. Individual. So you can find that value that Sienna is using here. Right? Similarity on drug, drinking, family event. Right there. So you might need to pull that out for some interpretation steps later on. That's when you find it. This will also give you, I mentioned the Jacquard earlier, this will give you the Jacquard as well as how much change there is, what types of change there are across the two waves. As well as changes, distributions of behavior, and changes in behavior. So there's that. All right. Now the other weird thing about Siena is that to specify effects, we're going to create a separate object that is the effects we want in our model. Okay, and here we're going to call that myEffects. And what it's doing is it's applying this getEffects function to this Siena data object that we created earlier. So look at that object. We'll do that. And then if we look at what myEffects is, you see it looks like it's eight effects. A couple of rate effects, high degree reciprocity. It's got effects here for predicting friendship, and then effects here predicting drinking. Okay, so these are our two different functions, totally different outcomes. Right? This is one outcome, this is another outcome. Okay? These are the effects that are currently in that we could use to estimate our model. Now we want to add more, right? We want peer influence. We want monopoly at a minimum. This step up here actually created a much larger data table that we don't see. Now, you can see it by running this effects documentation. And it pulls up this table that the idea is these are almost every possible effect that one could estimate given the data that you entered. So it's a whole host of network kinds of effects, right? Things like reciprocity, transitive triplets, different versions of transitive triplets. You want to look at the manual, see what those are. Recycles, transitive balance. There's like 800 effects. Right? Some of them are these network-based things. Some are based on drug use. Some are based on drinking. Some of these are here. Some of these are for creating ties. Some of these are for maintaining ties. Some of these are for constraining those to be equal. Right? So there are hundreds of different effects we could choose. Okay? To actually choose an effect, we're going to use this column over here that says shortening is a unique name specifies a particular kind of effect. So for instance, reciprocity here, transitive trip, right? Specifies a particular effect. And then we're going to, for some of these, combine that with other information here. So let me go around here. We've got drinking in the model, drinking in the data, drugs. We've got family event. For drinking, we're going to end up using something called SameX or SimX, which is people the same in their drinking. Okay, well, we've got a SameX effect for drinking. We've also got a SameX effect for every other individual act. Right, so we're going to combine SameX with drinking to create that effect. Okay. So what that actually looks like in our model is we're going to do something like this. Okay, we're going to take our myEffects object, which is the set of effects we want to include in our model, and we're going to specify which effects get included. Okay, we're going to identify an effect. Abstin is a similarity of your influence effect. Okay, it is going to be based upon friends, so the similarity among my friends. This could be other networks if we have multiple networks. And it's going to be predicting drinking. Okay, so we would run this. And if we looked at this myEffects object, we're going to see now for the drinking function, we have this thing called drinking pattern similarity. So what we're doing in steps like this is we're going to this massive table, and we're figuring out the rows that correspond to the effects we want to include. And finding that row and checking it as okay, include this one. And there's actually, let's see the column here. There's a column here that is included that indicates which of these are actually included in the estimated model. So 800 possible effects, some small subset actually gets included in the estimated model. We can actually look at this thing set up the effects. This is the things effects. We can actually look at that. The fix brings up a table here. You have to bring it up. I can barely do this. But there's a column here, include, that lists, okay, which of all these effects are included. Include is true, not include is false. Most are false. As we're setting up the model, we're going through checking these as include. So one of the, most, we have to stop this. So one of the challenges is figuring out how do you specify this include effects. And if you think that what I'm trying to do is figure out what row in this table do I need to include. I need to have the outcome variable, I need to have the right attribute based on this attribute, and this shortening here for the effect. I need that combination of things that narrow it down to just one row. Yeah.
How do you assess or account for multiple effects you're choosing? Would you run those independently before you chose your effects, or is that something that you're just interested in like the summary account of like you don't really need to separate out all these different data sets, you're just trying to see the
Yeah. So I think two answers. One is kind of theoretically, I'm trying to capture the main things that you think are happening, and not. And so the multicollinear, my mind was thinking about theory first. So there's different ways of specifying. You want to test all these different ways of specifying. That's a very real concern there. So there are two things, couple strategies. One is, and this is just a general good strategy, is engage in forward-fitting modeling approach, where for an initial estimation, don't put everything in there. You want to test. Put in key effects that you know are strong, and kind of slowly build up the model, and dropping effects that are possible controls, but don't really end up mattering here. So build up the model, and then so it's something like I want to test a bunch of different ways that certain things might work. It's probably not going to work for all of them. The way to detect multicollinearity is the model does converge. And so you can do a couple things. So you can test a score test for perspective effects. You can imagine make a base model, and I want to test these effects. Let me score test them, which is basically say don't include them, but figure out how much do they improve fit and get back a chi-square value. I can tell you some of these look like they would really improve fit, some would not. There's some direction you can include them. Evaluate them. You could, I think if it's not too many, you might try a couple of iterations in the same model. You may have the power for that. I've maybe once been successful in that, but oftentimes it does. Score test is the main thing. Are there other questions? Yeah, go ahead.
When you run the
Oh, where's that list of 800 come from?
Yeah, well, because I like, there's an effect from a different script. Like I have our script from my advisor, and he has an effect that I want to include, but it's not available when I, look for the effects that are available from the document. So I'm like, what is this?
Okay, okay, so it could be two things. It's possible if you don't have the latest version, maybe the effects are added all the time, it could be that. It could also be some effects. There are probably just as many um, interactions that you could create. So it might be that that's interaction. There's a way to specify. So some of these effects will go against commonly. You could interact with creativity. That would be a custom effect. You take these effects that exist and just say, let's put it together. Maybe that.
I can say that like it's the short name is effect from, the effect from, and I have it available for.
That's pretty. That should be in all of them.
Well, I have it available for like identity covariates,
Yeah.
so like gender and race, but I don't have it available for the network. So like what I want is the effect from the network on my behavior being a variable,
Okay.
and it won't get it.
Okay. Yeah. Let's talk. Okay. Anyway, because there's a few different ways that networks could come in. I wanted to keep it running. That never happens. You never see a model run so fast. Okay. So I did want to just run this again. I want to point out a couple of things while it's running. This screen pops up. That's Sienna. These are how the parameter estimates are changing for different effects. These are kind of correlations between jumps from effects, right? Sienna's trying to go from what if reciprocity is at 2? Right? How does the model fit? What if the 2.1? What if the 1.9? Right? It's jumping around for reciprocity and everything else in the model. And what you want is eventually those jumps get smaller and smaller. So these get closer to 0 and 0 and 0, which is a good fitting model, or promising. If these get really, really big, or these get really, really big, stop. Your model's gone haywire, and it's not going to fit. Okay, so these things are, for a decent sized model, this could be 2 hours to 48 hours. It really is. So if you can get some problems about it, you can do that. So the other thing I want to show you is, you're looking at the results. First thing to check, this convergence ratio. Right, this model, this should be less than 0.25. Right? If it's not, run the model again. You can take the current estimates as starting values, run the model again, get decent convergence before you start trying to do anything else. You've got convergence ratio overall, and then up here, you've got convergence for specific effects. It could be that you don't have this convergence, it could be one effect that's problematic, which could be a sign of linearity. You might want to pull that out and try it again. Okay. All right, I think I'm out of time here. So
That was a little more time if you wanted. We scheduled the break for coffee at 10:45. I was
I don't
impressed.
need coffee, but all right, so I'll
Yeah,
just
you can
mention,
keep people from coffee if you want. That's up to you.
I'm not getting coffee. I'm going to a couple of concluding notes. And then I'm happy to answer questions anytime after the workshop as well. Okay. So, well, I just want to mention there are like hundreds of things I could cover. So this tries to mention some of the directions that folks have moved in. Some of these are now totally possible. Some are still in development. So there's a lot of flexibility in thinking about how different processes come together, different objects come together, different behaviors come together, different ways of thinking about influence. Yeah, it's kind of a gold mine of opportunity. looking at the literature, right, is one of the best ways to understand for networks like mine, or as friendships or something, what are the kinds of things that people involve, what are the kinds of things that are important. And then using your own network intuition to figure out how does that work in my case. Yeah. So, all right. So last thing I'll say, we have peer influence on drinking. This is where we ultimately started. We have a model of selection on drinking. We don't get p-values here. We have to do some steps to get the p-values, but you can basically take the estimate, divide by the standard error. These are the t-distribution, so these are about twice the standard error. So we barely have enough. With 50 folks, that's not surprising. So it must be pretty strong for folks. We can do some additional steps to figure out how important is the selection versus influence in driving similarity. Right? We don't get too much insight here. These are on different scales. So this could be 90%, selection, 10% influence. It could be the other way around. So there's some further slides that talk about using the CNN, the simulation capabilities at the heart of CNN to do some kind of further work to try to understand the implications of the model. So one thing would be to decompose how much each of these is driving the observed level of similarity. All right, so I'll let you have coffee now, and please let me know if you have any questions.
Thank you. All right, yeah, get up, sort of stretch, make sure you're awake again early in the morning, get some more coffee. We'll be back here at, I'll be discussing simulations here at about 11 o'clock. So.
All right, all right.
left. All right. There's that point in the week where I wake up 100 times as bad jazz. All right, so we're going to sort of take the ideas of simulation that David gave us a moment ago, perhaps sign of bad judgment in a long day. But, Tom Schneider is a very generous and self-identified reviewer of our textbook. And in the process of writing the book, I pointed out that seeing it almost great. Really hard to do. Yeah, nature's complicated, you know. So yes, there are difficult things to them, but it's that flexibility that makes it so powerful. I think he's right in a little sense of that he's playing about that. So what I'm going to spend right now is the next, we have two more sessions left, 2 workshops. This next one I'm going to focus on, and you can hear me back on it, so probably not just me. But the plan is to talk about this notion of simulation, model-based simulations, or estimation-based simulations that David just talked about. Move on to this notion of agent-based or de novo simulations. So this is that one time in your scientific career when making up data is the thing to do. So we're going to talk about a smart way to do it. And this is a much bigger sort of project than we can talk about here. It's not really just network or maybe the network side of it is there. But the goal is to help you understand sort of the potential of simulation models, what they can be used for, as well as to try to give you a handful of cautionary signposts. Say, you may be tempted to do this, but think twice before you use it. So that's what we're going to do. Okay. So we're going to start with what, why, and types. We're going to go through a basic rubric that I've come up with over a while to think about simulation elements. Then we're going to effectively go through a set of case studies. So, and we'll end with a little bit of not so much an R code, sort of like I'm trying to give you a piece, but I'll point out some things. So you can make things up. Simulations run the gamut from simple randomizations, right, where you're trying to figure out what's going on, to a really full-blown model. So fundamentally, the goal is to make up data in a way that answers a real question. The kind of question you want to ask is really dependent on the situation you're dealing with. So the reasons to do it through simulations are probably the first biggest one. This is lack of data. You can't go out and get it. You'd like to have the data that exists there. I would love to be able to figure out how to do the population, but actually finding all the data out there that I need to do that at the level that I want is just impossible. It's also often unethical to do it, right? So one way I can figure out how to do the population would be if I could snuck someone into this room with, infectious disease and see how long they guys get in. But IRB won't let me do that, right? So I can't use you as human subjects to speed a disease or something like this. There are, of course, a million types of things like this you can do. People love their housing and so forth. And so there's a whole series of questions where the data is either unavailable in practice or unavailable for ethical or theoretical, realistic reasons of the way the world works. You couldn't possibly do it. I think more interesting in some ways are that we want to figure out simulations to extend theory. So we want to, the thing you're going to, the story, to give away the ending, the story here is the simulations are what you put in. The key is to put in there things that are informative. And most of the time, theories are informative when you have some complicated understanding of the world, lots of feedback loops, lots of processes that are contingent on each other, and it's too complicated to write down a simple equation for, to estimate a model on, but you want to find a way to ask how the process really applies. So oftentimes, I think, we as social theorists have pretty good intuitions, not formal models, of micro behaviors. Things like we understand jealousy, we understand desire, sort of things at the individual level, and how those aggregate up and how a reasonable feedback process is going to make the whole system evolve is really unknown. So we need to think very carefully about that. So in particular, I think that is that our processes of forming a network and the agents that do in the network have these built-in feedback loops. People I'm friends with, we start acting similar, our similarity selects us into other kinds of behaviors, and so that feature creates a feedback loop. It's really hard to model from a statistical standpoint, but then there's another feature, which is obvious, that you've seen a lot of this already in this workshop, which is statistical validation. So lots of times we develop methods and measures. We want to know that they work the way we think they work. And so oftentimes just doing Monte Carlo simulations are very easy to get with that. We do a lot of that as well. And finally, there's a lot of sample construction issues that we need to think about in these networks. Remember, the assumption of network data is that you have the full population, but oftentimes you don't really have the full population. So for cost reasons, or sample response rates, or whatever, you might have 80% of the population, you might have 40% of the population. So if you have a model of what that looks like, you can then simulate out the population you have. All right, so what are the types of simulations you can do? I think that there are a series of these dimensions that are no guiding theory behind these dimensions. You know, these have odd characteristics of what simulations do. So take that for what it is. But I think that these are three plausible things that you want to think about in dimensional simulations. First is like, why are you doing it? Is it either trying to predict something in the world, or are you trying to illustrate a feature of some kind of dimension in the process? So if I'm designing a simulation study so that the Social Security Administration doesn't run out of money, right? That's a simulation where I'm really trying to predict how many people are going to retire, how long they're going to be on benefits, how long they're going to live, what kind of dependents they're going to have, right? So this is a prediction kind of model. And that kind of model, it really needs to be grounded in data, very clearly validated that each microstructure to make sure that where I'm going is a plausible feature. And what I want to know is instead whether or not you're better off vaccinating kids in schools versus kids at home, then maybe that's a kind of illustrative process where I could set up a for example and have all of the basic elements of that process right, but I'm not trying to model any particular school. I'm trying to show that there's a difference between one small vaccination versus one mass vaccination. You have a version that is a grounded theory versus a database theory. So oftentimes what you'll do is you'll take a series of observations from the real world, this is what Sienna's doing in many ways, and say, how do I simulate from one observation to another and take the element in the middle that I don't know and impute what's there and try to figure out the best feature that will get you from A to B. That's a nice grounded database simulation. In many types of cases, that's the type of thing you want to do. Figure out how much data is there, and take that and move forward. In other times, we just have a theoretical set of propositions. We know nothing about them. So we really are making things up completely from scratch. So I have a sense, say that the Martians probably have homophily. I have no idea on Martian homophily, despite what the History Channel shows me. So I'm going to spend my time sort of thinking about how they select certain people and so forth. And it's completely made up, right? But presumably I'm doing it because there's something about the world that I care about, something about theory, say, reciprocity, finally, there's a realism question. This is a bugger. One of the things that people do when they're trying to figure out what they want to simulate in the world, they need to figure out how real they want it to be. Your instinct is going to be to make things real. I'm going to caution you to be really careful to have only the reality you need to have in the simulation. Because even the simplest of these simulations get really difficult to do. And so once you start saying, well, I'm going to model the spread of disease in workshops, and so I'm going to have a bunch of agents come into the room, I'm going to have a certain level of spread of disease, I'm going to put on this all the basics you might put in, and they say, well, I'm going to figure out where people sit. I'm going to figure out what color shirts they're wearing. I'm going to figure out whether they're eating the coffee at the same time. There's 1,000 little details you can put in. And most of those are going to be relevant. The real problem is once you get to that level of detail, you're going to end up with a mess. So this is a balanced process between ability and understanding and realism that again is competed with these other features. You predict, you might need more realism than understand or illustrate, but those features are there's a feedback in that process. So you can think about these dimensions of sort of realism prediction versus theory and data. There's a whole bunch of examples out there. So in the up in the far corner over there are things where your realistic data on realistic database models. I think sand simulation is an example of this. The EpiSim models, the Epi model simulation, which is a tool that Genesis developed to help you figure out how likely disease is to move on a network. We built it in an HIV context. That's really nicely built to be realist. The CoreSim model, which was developed for Social Security Administration, these kinds of models are really detailed, very grounded in data. Their goal is to predict the next year of Social Security, for example, a lot of the COVID modeling simulations, right, they've been all over the board. Right? So I put it in the middle here because of the ranges. Some of them that I've done for COVID simulation myself and Dana and the others in this room. This work was built purely on a toy model. Let's assume that masks work. Let's assume that vaccines work. There's a range of them. And then the mixing is almost random. You can figure out how much adoption affects the likelihood of a whereas when Jimmy Adams was working on the Colorado COVID task force, they were building departmental models where the departments might have only 2,000 people. Very detailed spatial and demographic department models, which was really much more realistic. So the purposes of that was very good. On the other, there's a really great demonstration model, and I'll show a couple of these as well, like the Charles Distribution model, which says, let's imagine that we have a very simple idea. People get to choose who they live next to. And what's the global implication of that simple individual idea? We're going to ignore history, we're going to ignore actual geography, we're going to boil this thing down to the simplest possible problem. What happens when you aggregate individual choices? And it's funny, that was kind of an illustrated image. For any given simulation, so that's all about frames. That's what kind of things you should do. Think about before you ever put anything in the world. Once you decide what it is you want to get out of your simulation, usually it has these three elements. First is an environment. There's some setting within it. In our case, that environment is usually a network. Right? But it need not be, like oftentimes it would just be an invited grid of spaces where people go. Or there's a famous simulation called Sugarscape, where ants are generating resources and consuming it at a certain rate, right? And so in that case, the population is nothing at all interesting. There's another great simulation that's been done on disaster response in Portland, Oregon, where they've literally mapped every address in the city, and they asked what happens when a flood happens, what happens when an earthquake, what highways can be on. So your environment could be incredibly real, or it can be completely abstract. There's something your agents have to move around and do something. Then the biggest piece that are probably these next two, which are your agents. The agents are the actors in your model that do something. There can be types of agents. In most of our cases, these are probably meant to represent people or people in organizations. But the agents are agentic. They do something. They make choices usually. So they engage in some behavior. Sometimes that behavior is as simple as being susceptible to disease and being sick and passing it on to someone else. So it might not be a particularly interesting agent. Other times, that they're balancing between lots of different opportunities they can do if you have a reason for why you might know how they would weigh those features. So the reason for how they weigh those features are your rule set. And so the rule set are the set of behaviors that you expect agents to engage in given the conditions they're faced with. And so there's always this mapping between what people should do and the situation they find themselves in. So it might be that when I get sick, when I start feeling a bit of symptoms, I stay home so I don't give my disease to someone else. So that would be a rule. Some sensitivity, some self-segregated features that the sick people have that should stop them when they're symptomatic from doing something. And so that would be an example of a rule. Another rule would be unless, if I don't have at least half of my neighbors that are like me, I'm going to move somewhere else. So that's the kind of rule. But it's always usually, it's usually the case that it's this intersection of a situation they find themselves in and the choice they have to make. The reason is that result of the choices other agents have made in the prior time. So that's what creates the feedback. So the idea is the setting creates the conditions for which the next agent has to make a choice. It's that feedback process. So a really fun example is the Schelling segregation model. So Schelling, this model I showed data here, Schelling had this idea, they were interested in racial segregation in cities. And the question is, what accounts for this really heavy segregation in the city? There's a lot of reasons you can't explain this. So you could go through the history of the city, you could go highways, who's an economist, so you want to see what kind of choices you make. So we made a very simple idea. Let's assume there's an abstract space. You actually do it in one dimension, there's models involved, two-dimensional models. But let's imagine that people exist on a space, and people have only a very simple rule set, which is that I'm either happy or I'm unhappy. These are the two conditions that people have in their head. I'm happy if my neighbors are like me. Some proportion of my neighbors are like me above whatever threshold we set. And if they're not, I move somewhere else. I move to any random open space. That's it. That's the only kind of completely market that completely immediate decision. There's no history. There's no other background. It's just exactly what's there. And so then you say, imagine randomly throwing nodes on a network on a grid. And in this case, this is, I'm going to show you this program in a second. It's not logo, but in this case, the grid is coded by the happiness of the agents. So here we have one agent, two agents, and if the square is solid, then they're happy. At least 30% of their neighbors are like them. And this wraps around, so that means there's a there. But if it's an X, they're unhappy. So in this case, this agent doesn't have 30% of the neighbors like him, so only two of them eat like him, and so she doesn't eat. So they're invaluable somewhere else. So you let this model run, it turns out that people self-sort into these really segregated neighborhoods. It's kind of cool because you might expect that threshold of 30%, and you would get up to 70% of my neighbors who would give it to me, and I'm perfectly happy. But in reality, what you end up getting is many people who have 100% of their neighbors that are exactly like them because they're not unhappy. There's no positive selection. Diversity, there's just an avoidance of being completely isolated in your own set. And you can change the setting. So in this case, little things you might not think matter. In this case, we started with about 202,000 agents out of a 50-50 grid, which is a pretty high proportion. If you make a smaller number of agents, do the same thing. You still see segregation, but not nearly as high. That's because one of the hidden rules in this simulation is that having an empty lot next to you is fine. And maybe that's not a rule you think you could. So that's a decision. It's a decision that the programmer didn't make accurate. It was a decision that emerged out of the limitations, or if you will, the exhaustiveness of the rule set. The rule set you give your agents are exhaustive, whether you need them to be or not, right? And so this is what and we ask for lots of bits, of course you get more segregation, and it's kind of fun to play with. One of the tools that we're going to use, and that you can use for this, is this NetLogo program. NetLogo is an agent-based modeling simulation platform, and it's mainly useful for illustrative sort of toy models. We will have there's a nice set of tools built into it for doing handling the data. There's an R version of NetLogo, so you can do some programming the data set. But this is the Schelling model, and so what's nice about it is the Windows interface, you can set it up, go, and you do set up, you can tell it what you want. So in this case, the density is 95%. A little bit less, I can say, there's a lot of empty set. Because this model is designed about the observed number of neighbors, you need to have a pretty dense set in order to make it possible to have neighbors that look like you. And then you can also decide whether you want to have most of my friends to be like, or most of my neighbors like myself, or a few of them. Set it again, and I can go once, you just step through it one at a time. So here you can see initially that everybody is almost, because I set this really high, almost everybody is unhappy. So it's very happy. And if you have a really high set, then it's not, it's not surprising. is that the I can't back up. You'll notice that some nodes that are very happy right now, these nodes, they don't have any complaints with the world that they're in, but their neighbors are not happy. So their neighbors are going to move, and when that happens, then they're likely to become unhappy because the situation has changed. Right? So that's the feedback process that happens in this kind of simulation model. And because I've set this threshold so high, and the network is so dense, that these edges, the boundaries between these sets are always contentious. So if you don't mind, if you let this model go long enough, it's just going to keep evolving until you get almost completely substantiated settings. You have this small and few pieces possible that have any meaning. Now what Schelling learned from this model is that it turns out that it's obvious that if I want a majority of my neighbors to be likely, that they're going to get segregated settings. But what's interesting is that even if I want to get a minority of my neighbors to be likely, it ends up being the case. So the percent similar observed here, in this case about half, is always much higher than the target. So this is the multiplier effect. Creates segregation. His point was that this is the sequential effect of prior choices the aggregated ways are often unobserved. So we would assume that you would get those kind of originating. So it's a nice illustration of that. His point from a social theory standpoint and a social justice standpoint was that it's not enough to say, I'm just going to have a few members who are likely, I'm tolerant of it. I mean, if you really want to get integration, you have to have more than just tolerance. You have to have some kind of an active push into avoiding or replacing. So, once you have this kind of simulation set up, how do you get it working? There are a few sort of things that people might not think about in the simulation, which are elements of your update rules. And so, in real life, people act in parallel. My decision doesn't wait for Charles to make a decision. So, I don't have to let him do something and I do it. Each of us is in the processor or has right all the time. And so, we run things in real life tends to work in parallel. But in programming, it might be important or necessary to be serial. So, for example, in the Schelling model, it's impossible for two actors to occupy the same space. There has to at least be some kind of a rule to make sure that if I choose an empty space, you don't also choose the same space in order for a simulation. So, it's often the case for a Schelling model, we'll program it serially just because it's easier to do if they want to have a decision spot, even though reality is parallel. So you need to think about how that. The way we typically institute parallelism, and it's really based by simulation, we actually use parallel processing. But what actually we typically do to simulate parallel processing is you give agents an understanding of the state at the top of the simulation, so everyone makes a choice in that is like acting as a What kind of update rules do you have? Do you update your simulation randomly, or do you update it in some fixed order? Update it randomly. Don't update it in fixed order. That's it. Just a visual. That's just my piece of advice. There's very few situations in which it's easy to say from actor 1 to actor n, just run the loop. But if you do that, then first actor 1 is always the first actor. If your data happens to be sorted by race or gender or whatever, then you're going to build in a sequence of effects that you might not use. So it's usually the case that you want to say, pick that actor random, but then do something. Again, it's going to depend on you do it. But the key is you need to think through your spatial data. This is part of the simulation. I'm going to sound a bit like a broken record. Every time you write a simulation, you have to remember that you are inventing the entire world. Right. So there's nothing given to you. So any choice you make, any implied choices that come out of the active choices you make are actively set. So you don't think through the both, something as trivial as let her actors in the simulation live and die and have births and so forth, right? The obvious point is, well, in nature, people don't know, and people die, and people are born, so usually I would have it's really hard to get good demographic situations. My interest is the spread of disease. Let's do a heart attack, actions, suicide, 1,000 other things that actually really exist in the real world. Because I'm going to have to spend 6 months writing a demographic population simulation to get that point right before I can ever add disease to it. So it might be better to say, you know what, I'm just going to assume that my population is fixed for the amount of time it takes this simulation to work. And if people can die from other elements, that's just a random variable in the edge. So I'm going to say that there's an observed death rate in my population. So those people can't get sick or pass disease. Right? So I'm going to simplify that out and all the other ones forward. Now, if I'm doing an HIV simulation in a country level, that's not a reasonable population. HIV moves slowly. COVID is a perfect reason. So you need to think through the process moving through the population that you have. If you do need to do a demographic turnover in the population, people from the vote and model, it makes sure that the biggest mistake you can make is that everyone ends up coming to vote at the same time. So you initialize all your agents as T1, and you assume they have a life expectancy of 50 years old. Not, but that's sort of something like that. Then you're going to find out that some group of people will die at the same time, and your simulation population is going to look like this, and that's a disaster. So you need to make sure that you see your population with an actual age distribution as opposed to everyone having age 1 when the simulation starts. Most simulations, and I am, as you can see in a second, this is the hot element of black. It's, there's always more things in reality than you can put in simulation. And there's often more, so the key element of the purpose of the slide is to think really carefully about the values and the number of parameters you need in your simulation to answer the questions you want to answer. And you want to identify the minimum possible number of parameters. Because every parameter you add multiplies the number of potential state spaces in the simulation. So if I have 2 parameters that have 5 values each, I have 25 state spaces. If I have 3, and 525 times 5 is now 150. So you end up with this massive sort of increase in the number of parameters you can do. Which doesn't seem like a big range, but it will be. You need to really be careful with that and make sure it works. The value of parameters is spend a little bit of time thinking very carefully about what region of the parameters is interesting. It's often the case that there will be values of the parameters for which logically it's interesting. So you can have a disease spread parameter. It could have a value of 0.4 or a value of 80% probability that if I have a disease, someone next to me has a disease. Or 90%. But those are uninteresting. Right, so at that end, if there's some bug goes into the population that has a rate of 80%, we're all happy. So there's no, you don't need a simulation. But there's some range of parameters for which the behavior is interesting, so that you can learn something. So spend a little bit of time thinking through your parameters one at a time, and not wasting your time focusing on that area where you You want some areas of your simulation that you check the code, right? So you want to make sure that when I set the disease transmission probability to 0, they'll be the same. I'm going to say it again. You want to have parameter sets in your model that you can turn the knob to 0 and get an answer that you know is going to be that answer. Because that's how you check your simulation. And so, for example, if I'm doing a network simulation, I will often test it on a pure fairly random graph. Right? That's not an interesting structure to me. My whole career is built around that random graphs kind of useless. But the math is really good. And so I can run my simulation over that graph. I better get an answer that's really close to the ODE so those are all the baseline sort of things that have to do with any simulation. What about network simulations? We like to think about network simulations in terms of simulations on networks, simulations of networks, and joint simulations of non-networks. Simulations on networks are usually something like a disease simulation. Start with a fixed, given population of nodes, or a graph that I care about because of the structures as it is. Then I will ask how something moves across those agents. It could be a disease diffusion, it could be an idea diffusion, it could be awareness of things, right? So that essentially your agents are constrained to interact with other agents in the network by virtue of the structure of that. So if these end up being pretty simple simulations because the network is a fixed object, literally aren't allowing the network to change, or it's changing, it's not changing as a possible feedback. So you would have observed elements of the network and you can do that. And again, disease diffusion is part of that. Simulations of networks say, well, where do networks come from? I have a series of behaviors. Agents move around randomly in the population, and I say, let them bump into each other, and if they bump into each other, there's some probability that it forms a relationship. So that's you have to set the rules for how they move, how they bump into each other, what happens when they bump into each other, is it an agent, there's reciprocity, so it's all these kinds of things that have to happen. These are, in general, when you think about how these things work, they are really two broad categories of effects in this taxonomy. First is an exogenous effect that we put actors in the same space. So we might have in our mind something like a neighborhood. So then if people have a neighborhood, then some people work, some people live next to each other, some people have dogs, right? And so you can think of things that would bring people into contact with each other. Those are exogenous to the information formation process. Then we have some endogenous features, such as a friend group. So if Alan and I become friends, and it's likely that Alan knows Lane, that Lane and I, we can build that in the mind. Again, decide what the stuff that's on the And then, of course, in most realists, if you have a realist system, most of these things are happening simultaneously, and often it's whatever's moving on the network is changing the formation of behavior of the network. So, for example, you're doing a disease simulation, this is an example I'm going to show you in a minute. It might be the case that if you and I pass a bug to each other, we both become sick. Well, there's a reason for us there's no risk for us infecting each other. We may have been out with each other. Right. We both have to we'll sit in our room and be miserable together, right? It's perfectly fine. But if, on the other hand, if I discovered I have COVID, I'm not going to come into the office and do that and make sure that it's kind of a model for us with a feedback process of right. So perhaps non-obvious contrary points. Think a little bit carefully about how you configure your network simulation to either keep it within theoretical bounds or within reasonable empirical bounds. Some simple ideas are things like degree constraints. If I have a network formation model, where I'm saying people are going to form friends through a lawfully or due to favorite closure, do I let them have as many friends as they can possibly make? Or is there some constraint on social energy? In most realistic settings, you're going to expect some kind of constraint. So it's going to be the case that I can't be friends. I love you all, but I can't be friends with all of you all the time. Right? So on any given day, I might be able to interact with, say, a dozen people. And you need to figure out what that threshold is, what reasonable kind of population you're dealing with, to think through that process. So is it the case that there's a constraint on the upward side? And that's, if there's not, you might have this problem of getting kind of runaway configuration. A friend of a friend can be a friend. If any person that anyone's connected to is at risk of being folded into a runaway problem. Another question to keep in mind is agent memory. Do your agents have a memory or not? And so most simulations, the one that I just showed you, for example, and walking simulations, a lot of these things are Markovian. The idea is that the state of the system at time t predicts the state of the system at time t plus 1. What happens at t minus x is irrelevant. So agents have no memory. That's computationally very useful, right? Because you don't have to carry a memory with your agents. So that's the real reason to do it. But you need to ask yourself whether that's harming your situation. break up, that's a really hard relationship. It's not that it never happens, but you will be cognizant of why it happened. So in that case, you know, the having already been dumped by this person is an attribute that they now have, it's specific to me, and so I'm not gonna go back for a second round of litigation. This is sort of a model, which we're making built into your simulation. Now, it might be the case that you don't care about that. You think that, you know, the memory process is epiphenomenal. It's really the case that once you break up with someone, your friends tell you what a jerk they were, and now you know how the information about the fact that none of your friends like your ex, and so that's irrelevant to what they did. So it's a process that you want to think about, figure out this in your set, but don't do it. Do it purposely. That's the idea. So make sure you have both sets of why. So if there's a, you know, I update this presentation depending on the year and what's happening, so we've probably done this now any time. These are all the kind of things that I've done over the years. I'm happy to talk about any of them. I'm going to talk about a few different case studies next. But just to give you a little bit of flavor of some of the work I've done, and we'll talk about the work that other people have done. So this is a very selective set. Questions or comments about the general process before I come into these case studies?
I've been trial by fire introduced to simulation work in the last year. I just want to add, like, one thing, what, like, I think all the like, considerations for setting up the model were spot on. I think one thing that caught me off guard, because I've tried setting up simulations and thinking about those things, but sometimes there are a wide variety of, like, tools out there to help you get started with simulations, right? But some of these assumptions, like we're saying, the population replacement, something that there are baked-in assumptions to how those tools are set up, and sometimes depending on your theoretical question, the kind of population you're trying to simulate, like it may not align with the pre-existing tools and how they're set up, and those tools may be more or less amenable to modification. And we, you know, in the work I've been involved in the last year, but I've encountered both extremes where, like, one, the tool's not set up for what we want to do, and there's a ton of modification that gets being involved. On the other hand, we've recognized the limitations, and we specifically designed our projects with those limitations in mind. I think, right, like gravitating toward pre-existing tools, right, is very compelling because there's so much done for you. But like, if you're gonna go that route, make sure it's easy to ignore those considerations you listed beforehand. And you want to remember that, like, you want to go under the hood of these tools and make sure that it is covering the bases that you need, and that you know, how willing are you to compromise? I think another thing with that I've said, I actually was talking about this with barbecue yesterday, right? But in the same way you were saying about, like, primary combinations, the more things you combine, compromise. Sometimes when you're studying populations, there are compromises. Like, for instance, you might be interested in a certain ethnic group, but I want to kind of echo what Ashton was saying earlier this week, that, like, sometimes the populations, or like the subpopulations of interest, might be so small that you have to kind of collapse them into broader categories. You know, in terms of discussion of, like, representation and talking about, like, the empirical implications of certain groups, it's not satisfying, but it's often a necessity that comes in this kind of work. And so that's another thing that, like, as you're imagining a kind of project like this, you wanna look out for, right? Like, if you're specifically, in Ashton's case, right, if we're talking about indigenous populations, you know, in these communities, so few data that it's hard to actually represent that. Like, if that's the case in the population you're trying to simulate, you probably can't do it, right? So, you know.
One of the things, one of the points I'll make at the end, you see here, is never sit down and write the simulation you want to do at the end. Write a little piece of it at the top. When you write a simulation, you're going to write micro pieces of it. Grow this thing in the code base from, can I generate a network that looks like a real network? Can I get things to spread across the dot? So it's like mind-numbing, instead of sitting down and writing from top to bottom, say, you know, simulation with evacuation routes and working. I'm going to make sure that I can figure out how cars move on the road. It looks like a road, very simple. question of using a simulation, the answer for me, a theoretical question, which is, there's this, in most of the bacterial and sort of disease world, we're used to thinking about simple contagion. I have the bug, if you haven't built up an resistance to that bug, we're in contact with each other, then you get the disease and pass. And it's really a dyadic connection process. Well, in social contagion, David Satola and Michael Mason came up with this idea of complex contagion. I only adopt behavior if at least K of my friends have also adopted. So there's some, element, and this goes directly on the idea of thresholds that Tom was talking about earlier before. So we wanted to think, well, kind of interesting to have this notion of complex contagion because the people who have two friends who could have adopted are not evenly distributed in the population. So there's a heterogeneity in exposure to the very routes that are possible to have complex contagion in the population. This little graph is an illustration of that. But if it's the case that these two adopt the network first, then it would be impossible for three to adopt the good at that time too, because only one of three this person's Red-Node's partners has had a disease. The only place that the idea to harm thinking about the disease. The only place the idea to move is two, but once two does, then three can. But then it gets stuck, because in this little pocket, there's never a chance for two outgoing entities to leave the population. So complex contagion seems like a very simple idea on its very first sort of notion. These two of my friends have to get the bid, or I can have to get. But it turns out that there are some pretty strong constraints built into the model by virtue of the network structure. So what we did is we said, let's imagine that we just see the population with pairs of people that have the good, and then ask how likely would it be for those bits to go out into the population and spread throughout the network. In this case, we can see that those are colored by their elected to adopt. So the first phase is the yellow and the green and the red and the blue and the white. These go to the edge and never get it. They don't have any two paths to the set. It's already effective or already very complete. And so this kind of constraint happens all over the network. And so we see this over and over again. And ask what's the ultimate distribution of adopting in this population? And it generates this really interesting bipolar distribution. The vast majority of new innovations in the idea space here fail. They just don't have to go anywhere. But you very rarely get these middle into adoption sets. Because once you cross over the threshold where there's enough for people to have two of them, you get everyone. So the structure of adolescent societies are such that most of the time a new idea introduced that has this kind of adopted set won't really take off. But every once in a while it takes off and it will always go everywhere. So going viral, if you will, in this setting, is a feature of the contact structure as much as it is a feature of whatever's going on. Now we're playing with this trying to think, well, what happens if you start instead of, one of the assumptions here was that I started with two connected nodes, and now you started with two disconnected nodes. You didn't start that at first, because the only way two disconnected nodes can affect the third is if they share that first one. So as an initial starting idea, it's actually hard for that to happen. But that's it as a set. You then ask, like, what's driving this and the underlying variance of the different populations? It turns out that it's the transitivity rate. So you have to have a fair amount of some kind of closure in order to get the set and for this curve is. But you have to also have lots of multiple routes in the network. Social cohesion is the thing that's really driving the set. You might think that when you have really high transitivity rates, you would end up getting lots of spread in the complex contagion. You actually don't. And that's because you have really high transitivity rates in an adolescent network where you really have like disconnected subgroups of very tight clusters. So they get stuck. So this is an example of using a simulation to really understand what on its face is a very simple sentence. The sentence is, I meet these two of my friends before I adopt. Well, that simple sentence implies something to the structure of the future.
So like putting that into context, like you would think of the jackpot situation, right? So the influencer probably had like followers. They were all connected because they were all following that same person.
Right, but it's probably even stronger than that. I think that, Google, YouTube, TikTok, they're not sending these ideas to random people. They're sending people who share exposure to similar types of others. So they're using these very ideas to construct who sees the bit and move forward. So the underlying promotion algorithms are probably building on something like that. But you're right, exactly right. In order for it to be taken off, you have to have at least multiple people who see it. And this was part of the reason, remember, that that Apple made all its products bright white. Right? Because the whole point was that if you're wearing a mic that's black, you can't see it. If I have white earbuds in, you can learn together on the bus, you see all these pairs of white earbuds out there. And so you get the fact that it makes it visible. And that was exactly that was an explicit reason for why they did it. They didn't make it bright pink because that was ugly, but white was visible and hot, basically. So this is it, that was exactly it. Right. Another example that has a little more feedback process is this idea of sustaining beliefs. So we have a series of models here where we said, we have our agents represent people. And the rules are two simple rules. Agents adopt beliefs from neighbors passively. So if you believe something, I also believe it. With some random probability, that's a weight, that's a parameter of the model. But at each time step, I care about that belief a little less, unless it gets refreshed. The logic here is something like practicing the language, right? So that I learned Spanish in high school, but right, so it's gone, it hasn't been refreshed. And I think this is a not unreasonable model for conspiracies, for religious beliefs, for other kinds of political ideas, that some of them are activated and reactivated. If they're not reactivated, they fall away, right? No one really cares about, Hillary Clinton's email anymore because no one talks about it. It's not in the set, right? So what does this look like? We imagine that process, you let me go into networks, most as you'll see from most of my simulations. For me, what's interesting is how that kind of a simple behavior model differs across different macrostructures and networks. And so we let this happen on a set of school networks, and you can see that there are some networks for which it's really easy to it's really easy to sustain the belief, even in the face of forgetting, because the network structure is different than others. This is not a great illustration, but the point of this slide is to show that despite the fact that each of these simulations, the parameter estimates were exactly the same, the network structure between the two had a greater or lesser read versus carrying capacity. And the thing that seems to be driving it is this average of structural cohesion of the underlying network. If you have a strongly cohesive network, the ideas keep in circulation, they keep moving. By virtue of keep moving, they keep activating the believing capacity. Now those are very sort of these network-based simulations. I have another slightly more complicated simulation, trying to understand how inequality is sustained across groups of populations. So in this case, we take a very simple social exchange game, and we play it with homophily. So the idea here is to be a population of actors who play a very simple exchange game. Exchange games are used in social science to represent social interaction sets. So you might care about when a cop stops a robber, but from a social exchange standpoint, that's just a police, that police interaction can be thought of as a high stakes exchange. Right? So everyone's exchanging goods, and so we can abstract all of these different kinds of exchanges, police or teaching or bearing or whatever, and just say it's a game. So agents have three attributes. They're in a group, they have trust for their own group, and they have a bias and they have trust both for themselves and for others, and they've accumulated some wealth or some value of goods. The key element is that group size is different and trust is dynamic. And so wealth is an outcome of each interaction. I'll show you exactly what I mean by that in a second. The rules are really easy. Here's a value given to you randomly. Each time you meet, you flip a coin, and you flip that coin that's weighted by how much we trust each other. So if we trust each other a lot, we're likely to get a positive interaction. If we don't trust each other a lot, we're likely to get a not positive interaction. So that was a simple way of saying what this is what each agent faces. So each agent faces a trust situation, right? And so when we first meet, there's no prior history, so I don't trust you anymore or not. It's just whatever's there, right? So initially agreeing with each other, and so that's a baseline trust here. And our here. So that baseline trust data is at some level, is based on this set. And then at each interaction, if I win, then I trust you a little more, and so then our weight goes up. So if we have a positive interaction with police, then it automatically takes that the next time we interact with police, I feel better about it. Trust me, it's the interaction with police. The goal of this set is to try to inculcate an idea of sort of self-fulfilling prophecy or other kind of feedback process where we like each other and things are going well, it continues to get better. If we have bad interactions, we distrust each other. But we want to put this equation in stride, so we have an in-term baseline trust, an outcome bias, and this thing called bias decay. So, for any two groups, this is set up, in this case, we have in-group to group 1, in-group 0, 1 to 0, 0 to 1. This is a two-group model that we're here. My thinking is that people learn from their interactions. And so if you have no interactions, my bias covers positivity. My in-group might be, I have pretty high trust people who like me, but I trust people who are not like me less. So that's all this is. But if I get a lot of experience, eventually my bias goes away because I don't need a bias if I know you. If I interact with you many times, then it's the case that I can choose my knowledge and not my bias. And the models worse actually if I can get rid of bias decay. This is a generous assumption for me. Excuse me, I apologize. Whenever my voice is problematic, for you, it's probably worse. So, but imagine this thing works like this. This model works kind of like this. So the simplest possible situation, right? Everyone, there's a mixing matrix of zeros and ones. They're all the same size. And the triangles are all the same. So each time we meet, we flip a coin. And when we flip a coin, we get a random accumulation. And I believe that people are generally good, and so it's a positively biased. And so on average, about 60% of the time, when I flip a coin, it'll be a win. 40% of the time, it'll be a loss. And so that means that 60% of the time, the move will go this way, and then you get up to like 80%, and 90%, so forth. So most of the time, you get this positive increase in exchange. So each line represents a pairwise exchange, so each one I, 1 day. And as you expect, most of the time, for each person, it goes up. Not always. The world is a random stochastic place, and some people, once they start losing, right, they continue to lose. So this pair of people don't get along very well. Now, if you then aggregate up across that network, you see that in this particular case, everyone's making money. Everyone's doing fine. Well, that's what they call it. They're doing flush. Now let's imagine that a little more realistic situation where we have equal-sized groups, right, and they both have the equivalent trust for their own group and equivalent distrust for the other group. And so in this case, as you would imagine, the pairwise interactions are much more positive in group. So we get an in-group pairwise interaction is positive, in-group pairwise interaction is negative, very positive, and between-group interactions are negative. Finally, I didn't set this parameter so huge that it's completely swamping, but you get more negative interactions between group and in-group. And what you see is, again, positive from the overall effect, but not as strong as it was before. If you pay really close attention, you'll see the axis drops a bit, and you get a slightly more shallow slope. Now let's make a more realistic situation and assume we have a majority and minority group. So one is zeros are a majority, one is a minority. And so there's a difference in group size. Again, if we said everything is equal, same kind of process, you get no difference, so there's no negative decline. Then we said a little bit again, each group trusts themselves the same, and distrust the other group the same. This is a very generous model from a service standpoint. The model is a race interaction. And in this case, if we run the model, we see the same kind of dyadic effect. We end up with lots of in-group effects that are positive, lots of in-group effects that are positive, cross-group effects are negative, cross-group effects are negative. Then if you look at the accumulation across the population, you'll see that this situation leads to much more negative outcomes cumulatively before the outcomes. Why is that? Because group size ends up accumulating. So if you think about what's the basis of the impact of group size, the minority group has fewer opportunities to win than the majority group. The minority group is faced with massively more distrust in the population as a whole because of the difference in group size. And so you get this amazing multiplier effect. And even though everyone is behaving exactly the same, it has a much more negative impact on the minority population than the majority population because of the differential access to that sheer unit result. So I like this model because it allows us to think through how you might fix a process like this. So if you're starting with something like this, where you have the simplest of possible exchange models, the baseline sort of interaction rate is going to lead necessarily to structural inequality because of the differential opportunities you need. What do we have to do to fix it? Well, one solution would be to say, let's buy black. Let's have a campaign where we increase the winning rate and keep everything else the same. And we could do that. It ends up being basically that it has to define a different set of probability spaces. So now you have one term in the in-group set for whites and the out-group set for blacks. But notice that at the time of the zero here, we just set the win probability in the in-group much higher than the time zero win probability in the first base. You can play these kind of games to figure out what it would take to win. You have to really crank up the in-group set in order to get a match with the other group set. So what I think this tells me is that if we want to alleviate structural inequality that comes from the baseline differences in group size and opportunities to make positive and negative interactions, that if you're going to do it, you're really asking the minority group to do a lot more stuff, right? They have to really overcome, and you work out the math of this, the size of this coefficient has to effectively be proportional to the size of the difference of the two groups. In order for that to happen, the smaller the group is, the harder you have to make them work to succeed. And that strikes me as probably a really best effect. And so we might have said one purpose is in the off diagonal, so that's the kind of thing you can work with these models. All right, one last case study that I think is kind of fun, which is more relevant to this group than to the others, is and this is meant to be a little more realistic in terms of the way these models work. In this case, what we're doing is we're trying to understand disease spread. We want to have a behavior feedback process with disease spread. So whether our environment's going to be village or rural networks, we're running it over observed networks. People have a full slate of demographic, economic, and activity sort of analogs. So you're going to try to treat people as if they're real critters as best as you can in the data you observe. And then we're going to layer over it two kinds of models. First is the biological model, which is a simple SIR infection model. And these two cases, one is HIV and one is COVID, is the kind of examples we run. And the second is the social behavior. The age is nested in households, they have jobs, they're engaged in neighborhoods, and all these things that are engaged. So the process is that we have sort of simultaneous evidence. Everyone's sort of living their lives. So we're trying to build a pretty realistic model. This implies a huge parameter space. That's why I'm showing this example. If you want to make sense of what this is, we have disease parameters, we have network parameters, we have active constraints, and it's really easy to walk yourself through situations here that are nonsense. And so in order for me, when I deal with a problem set where I have lots of the event is a probability, I have lots of variables leading to that event, I always convert it to a logit equation because that way I don't have to make sure that all of my tiny bits add up to less than 1, right? I just let the logit equation do that for me. And so almost all of my parameter space models are going to be something like this. And what this is doing is this is not an outcome. This is literally a map of the parameter space. This is what's saying what's the level of an individual diet. What's the likelihood that an infected contact is susceptible at this level of biological level of transmission? What's the likelihood that it would be transmitted? And that's conditional on the strength of the tie across the columns, on whether or not they happen to be sick, they're highly likely to pass on these scenarios. As more of their friends become sick, they're going to essentially pull themselves in and interact with other people less as the way the simulation is set up. So they're unlikely to pass it because they're going to be self-aware and not communicate. If they feel sick themselves down here, they're going to stay home and do less. So the difference between this 0.8 and this 0.35 is self-selection of elections. And I'm not going to be infected unless I feel crap. But I can, and that's easy for me to stay home when my weak tie, but I still have to stay here with my wife. Right. So my strong ties over here, actually, they're at higher risk when I feel sick because I can't avoid the disease. So that's why you see this going up in Chicago. I might care about it more. I might wish I didn't make this thing. But I wish there was this correlation between strength of the tie and the individual strong tie. We expect it to be that way. Then there's a population, sort of independent population effect that if I look around in the world and see the news, and I don't hear a lot about people being sick and going out and sailing, if I know there's a pandemic going on, I might really be sick. So I try hard to. So this is sort of what this world looks like. This is the world we define. In this case, it's just these 5 dimensions. Then we run the SIR over, and you get these kinds. This is just a cautionary tale on how quickly you can get lots of different results and you have to parse them. Right? This is what no social feedback at all looks like. I have one parameter set where I've set the coefficient to 0, so that your sick coefficient is to 0, the population coefficient for 0 is sick, and then in this case there's no symptomatic effect. So this brown line is what my biological infectivity rate is in the body. So everything is effectively relative to that. So then what I do is I go through and think about how these different features matter. I would go through and ask, well, to a biological only model, if people are really receptive to the population being sick, and really receptive to the group being sick, then you get a much lower effect. And you can gauge how that works. This is the game we're playing with this model. This model is not done yet. This model is in the process. So this is what we're trying to do is figure out effectively if I'm better off advertising from the population model and say if the probability of people not engaging in not having an infection is sensitive to the number of other people in the population that are sick, then maybe we just advertise the extent of and that would be all we have to do. That's what this difference in cost of control is. In this particular simulation, it looks like it's on control doesn't have a huge effect. So maybe my parameters are wrong, maybe my theory is wrong, but that's the kind of thing we're going to care about, trying to figure out how strong the population slope has to be before my awareness of the population would make it likely that I would have it unstable. So these are the dark things I'm not happening. Notice what I'm not doing. I'm not fitting it to an actual disease cycle. Right? So although there are realistic elements in this simulation, this is not a realist simulation. I'm not trying to predict the next event. I'm trying to predict how the model, how the behavior is different if people were more or less reactive to the local effects of the situation. Right. I'm out of time, I think. But in the slide deck, there's a series of pragmatic points and software you can use. I really do recommend, if you're just getting started in this business, play with NetLogo. It's not quite as shiny and new as R is. One of the nice things about it is that it has all of these models built in there. And the NetLogo language is English. And so you can actually read it, various kinds of weird functions or whatever. And the simulation code to run a Schelling model in NetLogo is only 80 lines long, including the comments and all of the display things that are there. So the actual model itself is modular, it's very easy to set up, comments can change, elements of these things I can go and do it. There are network models already built into NetLogo, so this is a diffusion of a virus-like simulation across a simple model. And so you can set up the different kinds of curves and ask how the might move to a very simple model. And it all is so it's a very good model to learn how to write a simulation. And it now has some there's not lots of nice pieces. They also, because it was generated with the idea of being a teaching set and have all kinds of different elements built into the information for it, because what it is, how it works, why it's being used, things to know that it's a very nice teaching tool to understand how simulations are built. If you want to go in and take the NetLogo model, for example, that's shown, instead of having two colored tools, you can have three colored tools. You can just go in and literally set up, in this case, the colors would be white or not, right? So I can de-estimate this, right? If I'm going to start one versus the other, I can just switch that around. If I put an add, it would work, try on the 11. But anyway, you can go through, you can change these things really easily. I am over time. The questions and comments, right? Because I'm speaking next. I want to speak for myself. I encourage you to play with simulations. I think that one of the things that's great about simulations, even if you never publish a simulation, is the process of coding makes you a better coder. I think. But I think you're a better thinker, a better theorist if you have to write down and force the machine to do what it does. And quickly discover that your understanding is probably not.
Okay, so this is not a technical question, but I do wonder broadly, and I feel like you already speak to this, like, why is agent-based modeling and simulation modeling, how did it really, like, develop or grown out of network analysis? Like, what's the, because it's not always gonna be about these direct people-to-people connections. I've seen simulations that are not based necessarily on people, and so I'm just curious, like,
Yeah,
what's that evolution?
yeah, that's a great question. And the main question is that most of the agent-based modeling on networks came out of this problem of processes on networks. The point was that you never have data on processes on networks. So in order to understand things like the spread of something over a population, Tom's gone out and collected actually data about adoption in the real world. But for lots of settings and for lots of things you want to do, you just can't get the data. So people start with simulations because the data was just so bad. And particularly early in the 90s, we had to kick off news with essentially disease and trying to understand what the effects of the kind of structures were. We were shooting in the dark. So the tide of the agent model networks was out of that hole in the data. Once that happened, people were like, wait a minute, there's a lot here. We can do something with this. And so these two populations of agent-based models and networks started differently. But I think they really crossed over with people came to recognize that in order to answer something like the HIV epidemic, we need to understand at this micro level how these different transmission choices impact the pandemic. That feature pushed the model in the direction forward. And then once those elements developed, people recognized the ideas, groups, organization, you turn it on the network itself. So then you start just the network is being adopted to the framework in order to answer.
And what is the APM framework? What displays that?
Yeah, that's a much more interesting that's a great history. So I don't know it particularly well. I have a very biased view of it because I'm coming from it.
Okay, so it was separate from, I thought maybe that it had kind of evolved from the network.
Yeah, they were parallel movements.
Okay.
And there were lots of systems things happening, so traffic and nature simulations would always be beautiful. And you probably did this in junior high where you have birth rates and death rates and so on, and then you look at the population moving bus, right? So those kinds of models were coming out of the 60s, and then the Shelley models coming out of segregation, and single cell enrollment, and the whole series of those were thinking about other kinds of social mobility processes. The best agent-based modelers these days are probably not in networks. They're really dealing with things like disasters and traffic and military simulations. And so those folks, they have network pieces built into them, but they're not necessarily.
It's bigger than like systems science.
right? And so, there's one of my favorite agent-based model actually is of the earthquake model for earthquake and tidal wave models for cities. One of the things they discovered was that if you can make some reasonable assumptions about how people are going to evacuate after a warning for a tidal wave, that everyone getting in their car is the worst possible thing that can happen. For some people, they should be walk. They shouldn't fly. Now, the model shows that from an agent-based standpoint, you can really that each actor makes choices. It's also ends up being a user-friendly situation because although the optimal choice is that everyone should, let the people who really need to drive, and everyone else should run on foot. Each individual wants to get the hell out of here as fast as they can, stuck. Right, so, but that was talking about.
Something related to, based on, the chassis based on the analysis.
Right.
And I wonder whether that makes it also implies that,
Yeah, so in this case, exactly, I built this cumulative mean loss record that people carry. And so that's what that curve is actually defining as a memory function. It's like, do I trust you? So initially, no. Initially, it's just, things one said, the more experience I have, I can move up and down. So you might be the kind of person that, 100, and there's a lot of them. But one of the other things is that it's just a summative memory. So it's the fact that you and I are going back and forth and cheating one day and cheating the next, cheating one day. It all balances out to zero. That's probably not realistic. Probably the case that if you're not reliably trustworthy, that I should trust you. But that is one more parameter module I can exclude at this point.
yeah, so, there's kind of like,
Right.
that also keeps tabulated based on time.
Right. And instead, what you could do is let's just keep the weighted function of the last 10 interactions, right? And say that, if you might, your argument might be that the higher the variance in those last 10 things, the less trustworthy, despite the that I should be a little less trustworthy. That would be a perfectly reasonable model. I don't know how we'll affect this outcome. All right, the last session is again me. You get very, very more me. And what we're supposed to, what's on the schedule is an open session, and to think about the future of network analysis and how. And I have some slides I can go through and talk about, some more I can broadcast more, and show you what Moody thinks are the priorities should happen in the next month. But I'd really rather not. I'd rather open the floor and have people ask what questions that are burning you, some of our experts in the room who are working in this field for a while, my suggestion they think is important, and have a discussion for the last 45 minutes of this conference to think about where we should go next, what we should do. So I can go either way, and this is why I didn't put anything hard for it on the schedule. If you want me to continue broadcasting, I'm happy to do it, but you might be a little tired. So I'm going to open the floor now. Force myself to be quiet for at least 2 minutes, or at least until someone else says something. The questions about it, you now had 4.5 days of swimming in efforts. Like, what's the burning question of the left? What's left open at this point? Do you really wish we had talked about? You haven't heard an answer for it, you want to go next? Please. The question was the most pressing future methodological questions. There are so many. So I think that there are a handful of things that are we're getting really good at. So the evolution over the last 20 years, 25 years in Siena, in Ergo, in Bayesian Ergo models, and other kinds of models of networks, and how behaviors on networks, whether it's the auto progressive model, aka LMs, network operating models, where they're doing learning at the same time. For statistical modeling of networks, it's still hard to do. that needs to be done on the edges of that, but I think that's in good shape. The real problem with that will be scale. So you're gonna get these models that we have for, 2,000 nodes, or 200,000 nodes, or 2 billion nodes, is something that's a lot. And particularly people are interested in the spread of things on online networks, you need to be able to scale. So online networks, and other sorts of social media type of networks, they tend not to matter for physical health. They matter a lot for mental health. They matter good health. There's lots of reasons that these online constant networks are important. The kind of tools that we focused on are insufficient to do this. There are other tools for them, but they're coarse. They're pretty powerful. For the kind of world that we're working in, and the kind of stuff we have folks in, I think the next foundation is really to go back to some of the ideas that we had originally on those multi-relational networks. And the good news is that there's a new buzzword for multi-relational networks, multi-layered networks. And now they're putting a name on what it is, more interested in it. And so that's good. I'll take the win where we can get it. But we started, the network field in social sciences started around this attempt to formalize and make explicit our understanding of really rich tapestries of religions. And that quickly ran in like head on into this practicality plus. And so the goal of doing these rich community studies, the problem is that none of you can get a career by going out and doing a community study. You can't afford to spend 6 years living in some town in Midwest Ireland to write up this refugees thing. We don't have an academic career that allows that to happen. But we still want to have that level of detailed understanding. It's finding a way to regularize, routineize, and efficiently analyze large-scale multi-relational networks, I think, is something that's an we have really good theory from social anthropology and the old theory from sociology and so forth to think about that, and great insights coming out of local members, working Mary's Falls, and other sort of people who are thinking about the ways in which networks are coding and living with each other. But I don't think we really have any formula on it. Nor do I think we have, we need something, I think, and I'd love to hear what David what you think about this, and Tom, what you think of this, but I think we almost need a natural history of networks, or natural history museum. Sorry. And the beauty of biology and natural sciences is that it's pretty reasonable to go out and figure out what a new species is. We don't really have as much of that anymore, and we started to. That's what those big, beautiful diagrams of small, villages were about. We don't have it much of that reach. So I think thinking about this ethnographic sensitivity with the quantitative rigorous analysis that is the improvement that I would like to see. Again, this is movies. You're getting a very biased view of that. Tom, do you have ideas of what we need to do?
Yeah, I mean, obviously, I would suggest that we're gonna learn a lot by doing network interventions, right? And then being able to model what's happening to that network over time when we purposely intervene on it. I also think you're right that being able to scale a lot of our approaches is a big challenge. There's been some work with, that large scale, LinkedIn experiment, where now you're talking about tens of millions of nodes. And when you talk about tens of millions of nodes, you're talking about hundreds of millions of links. And we have really good tools for looking at smaller networks, but, to get to that scale is a real challenge. So I think those are two big frontiers that will offer a lot in understanding what's happening in society. I also think somebody ought to do a history of network analysis, because the field has fragmented in some ways. There's a lot of different streams, and it'd be interesting for somebody to do some kind of oral history and ethnography of what's going on. Those are just some of them. And there's a lot. I mean, like you talked about the social media stuff. That's a huge trove of network data that has strong implications for what's happening to people's mental health, political polarization, misinformation, disinformation. Finally, Francis Collins, the director of the NIH, released a statement about 18 months ago saying, we really blew it when we released this vaccine stuff because we never thought about the communication problem. And he was one, when he founded the National Human Genome Research Institute, he very specifically demanded they have a social and behavioral science branch. And he said, we're gonna figure out what the genome does. We're gonna understand these associations. We just don't know how it's gonna play out in society, right? And so what you see now, of course, is we're gonna get vaccines, we're gonna release them. Our assumption as scientists is everybody's gonna love them. These are great, it saves lives, right? And then what happens, it turns into a political football. And now vaccines of all types are being questioned. And so there's a lot we can do around network analysis to address very serious societal and in my world public health problems that demand attention. And we've got a lot of work to do. And hopefully we'll start to see more funding in this direction because I do think it's a way to address these problems. Yeah, very explicit.
Yeah, I was just gonna second. I like the Natural History Museum idea. I would take my kids. But seriously, I've done secondary network analysis for so long, but recently I've combined some interviews and ethnography, and it just leads to questions about what's happening within context that you may not even imagine. So I think combining the mixed methods really is something that we need to do a lot more of. And the second thing would be thinking about time. So many of the models I think we talked about this week are all panel data. But network processes, the kinds of things we're talking about, health changes in health, those happen on a much finer time scale that we're not capturing. So we've got network models, relational net models, as an example of how we can monitor or test for changes in relational different aspects of relationships over moment to moment time scale. And so kind of combining those with the kinds of models that we have that get at longer scale changes in relationships or changes in statuses. I just think that in terms of the methodologically, we can do more to try to get at both of those time scales.
So I have a question here. Please. Yeah. So one thing I noticed is that presenters use a lot of smaller community level data. I think those are really helpful, like in a program level. I think in my experience in my work with in working with federal policy, I think policymakers or decision makers are more comfortable using bigger data. They're a little more comfortable in making decisions and those decision processes that happen. So I think I know surveys are super expensive. I can just imagine if you want like a national survey that's specific for network data, that would be really costly as well. So I wonder if you're seeing a bunch of methods of how to collect data, big data, that are, I don't know, way smart.
So I think there's a couple of answers to that. I think you're absolutely right. The scale issue is there. I think that there's a big push now for trace data. So one of the movements that we had is coming out of some of the woods of SafeGraph and Google for Good. Like these kind of folks were putting out data that they didn't have to put out. Those data allowed us to look at who users when place connects are using networks. So we can get some sense of at least where people are coming in contact with each other. So for things like diseases, that's a reasonable underlying network. These structures probably not going to help us a whole lot, right? But there are lots of other kinds of traces that are out there. So if we know that the bipartite network of what people consume on media, then that's going to tell us a lot about clustering and the range of different community dynamics that could be out there. And those data exist, right? So Google has all that data, they're just not sharing it. So we have it. The second answer, I think, is that the world is big, but we don't try to go out and collect, like, when we become a full political events or something, I don't know whether it's good or not. We don't survey every person, right? We only do that every 4 years. We sample, and we have a way of sampling that's effective for aggregating up individuals. That is something that is for network.
I want to jump in on. I totally agree with that. When we were talking about the I work with large networks all the time, and one of the things that I'm often spending a lot of my time doing is actually identifying the relevant subset within the network that would need help. And in my space, we can do shortcuts like stance detection and things like that to identify that. But having principal network sampling techniques to extract the relevant subset, because in fact, even phenomenon like going viral, you go viral actually within subcommunities. Like, look, there's things that happen. I worked for 3 years on GitHub data. There's things that happen on GitHub data that go viral, but no one else in the world knows about it. It's weird, right? But it's a real viral process, and it's a super large network. I'm totally there that we need scaling issues, but you don't actually need the network of everything. You need the relevant network to your research question. So getting good, learn the ad hoc ways of extracting these relevant subnetworks and making stories about them, and we try to be a little bit more principled about these stories, but it does make me nervous and all work. And so I would interject is, yeah, let's include sampling theory for that.
I think the beauty of most social networks are they're big, incredibly sparse. Most human networks, Dunbar showed a long time ago, most of us live in a very small interactive space. The number of people that we actually interact with scales, literally to the hard stop where the population is growing up, the possible space goes up to the square. So there has to be a sensible sampling strategy. Even networks go a long way. A lot of the processes we're using today aren't even. So two-step even networks might be all we need, but I don't think we've done the work that makes it really clear.
I was curious about, like, I know at the beginning of the meeting we spoke a lot about like the ethical considerations, but especially looking at like online data where like private companies can purchase so much metadata, but like that's not data you can probably collect or pass through an IRB, or should you maybe? Like, what is that balance between like the ways in which IRB should adapt as, there's just so much data, or should adapt to what's going on and what you can collect versus like, especially if you want to do speed ranking or some type of like dispelling missing misinformation. That's information that people can purchase, but you can't necessarily pass through.
Yeah, I do think that something, this is the question that I certainly can't answer, and we as a field have struggled with. My sense is that we can walk the years and try to fight for anti-China back years now. The kinds of things that private companies get away with in terms of collecting data, which are particularly harmful, and people volunteer doing all the time, we can't do. And so I would argue that in many cases, in many sort of situations, that it's the IRB sort of hyper concern with treating all data as if it were your medical tests, as opposed to of course, there's a lot of rules that you think what the actual risk is, as opposed to the cumulative benefit. Now, I think that it's going to be really hard to draw that line, and it's like if you've ever dealt with a medical IRB, they are not flexible people. Right, and generally, I'm sure individually they are, but as an organizational collective, because no one wants to be the person that comes out and says, yeah, do whatever the hell you want, you'll be fine, and then have something bad happen, right? And so, it's always easier to be it's always safer to be more and more restrictive and more sort of set. And I think that we no longer live in a world where people have a reasonable expectation of privacy in every day. You've probably walked through 100 cameras before you got from the hotel to here, right? So this notion that, and certainly, Google follow your phone the entire way. So the sense in which, we are used to thinking about private behavior and private set sort of completely anonymous away. There's this whole range now of activity that is semi-public and certainly public to a certain audience that I think that it would be nice to be able to have some way to, I could imagine a social goods tax on information that says that companies are already collecting this data, they need to find some way to make it available for us to use for public good, or you're not allowed to have a monopoly on that data anymore, right? So that would be a perfect, making something, I have thought about that idea all of 2 seconds now. But you could imagine that there's going to be some kind of a compromise between private profit and public good that comes out of this. It would be quite useful. I mean, when mpox first started popping up in New York, there's no way that you know, the dating apps that are already there wouldn't have been, if we had had that data, it would probably be much faster at being identifying what the risk set is for the spread of those kinds of diseases than would be otherwise. I don't even know who's having sex with who, but knowing what the structure of that network looks like lets me know whether or not this kind of a STD is going to be really dangerous or nothing to worry about. And so thinking about those kinds of features, you know, why not make that data available in reasonable ways to researchers to do something? Please.
So another question related to the collection. I was wondering whether in the network data collection, whether participants can actually have more agency in terms of like collecting data themselves and also reporting data or donating data themselves. So I listened to a presentation. I think that was data donation initiative that took place in Europe, but that was related to the health and also fitness and location data. For respondents to donate data voluntarily themselves. So I wonder whether that could happen in the network data collection, and also like for the time use data, respondents can document their time use themselves so that respondents have more agency, or like our population of interest have more agency in terms of documenting their network structure.
For those who couldn't hear in the back, that's a great question. The question was about whether or not there's opportunities for data donation. So it would be possible for people to donate and create a public archive of network data. In much the way they do with time use data and other kinds of biological samples, sort of this public science idea that where people are doing citizen science and helping, you know, observe bird watches or whatever. Yes, I mean, you know, I mean, if you would, I think you should start it, right? The hard part there, and this is still an issue that I think that for a public repository of network data, is that if I'm reporting on my reactions with you, but you don't want it in there, is that fair or not? And so it's because it's not an individualized choice, it's a little bit harder. On the time use side is easy. That's like, how I spend my time is fine. Whether I'm identifying other people while I'm at it or not is still a question. Now, I'm on the liberal side of that idea. I think it's fine. Like I'm not going to, if I, you know, but I think that that's something that the field would need to come to a decision about that we haven't yet. Please.
So in most of the examples we've seen in the past days, we're dealing with network data where each node represents an individual. I think we've seen some alliances across countries, that was only. I can remember that's not the case. But I work primarily with inter-organizational data, like government agencies and nonprofits working together on social justice issues and things of that sort. I just wonder like what your thoughts are on inter-organizational network and research opportunities in that area.
Yeah, the good news is that inter-organizational network data is a well-trodden, very well-developed field. So there's plenty of people doing out of it. It's a bias of the people I know and arms I can twist to come here that you're getting mainly individual level data because that's the data we're working on. And there is something of a bias, I think, in health field where we focus on people getting sick, right? So we've been doing this, but there's I strongly encourage you to go check out Journal of all the Academy of Management journals. There's a bunch of work there that's been done on inter-organizational networks. And so that's where that work is happening. The main thing about aggregate networks is that a lot of the theories that we've talked about in terms of network formation and dissolution and transmission processes are predicated on the idea that people control their relations. Yes. For organizations, it's a committee that controls the relations at best, and it might be, you know, and it's often variable internal to the organization. So inter-organizational networks often make this assumption of a unified organization that is a node, when in fact it's a network within the organization of people that are doing things, and you get a cumulative decision. Right, and so you end up with this weird multi-level network of networks thing that is kind of hard to deal with. And there has been some great work on that, which I'm just going to draw a blank on because my brain is fried, but on the author that I should be remembering. But anyway, yes, so there is work on this. I think that you're more than accurate to point out that we haven't covered it here. That is a failure on our part, not of the field. So there's plenty of work out there to be done. the good news is that one of the things that I love about the network paradigm is that it's a transposable abstract data object. And so much of what we talk about is applicable, like it's called community stuff, the transmission stuff, all of this. It's when you start thinking about the theory that drives why the organization changes that you just want to be a little bit careful that, you know, a friend of a friend is a friend, but, you know, a business associate of a business, you know, a company's exchange partner of a company's exchange partner, there's no real reason to think that they shouldn't be competitors, for example. John?
To drop a buzzword for you, look at computational organizational theory. Organizational theory, the CMU School of sort of organizational network stuff. That there's a whole bunch of stuff though. There's really simple companies competing with each other and ecological approaches on one hand, and then there's intra-organization looking at formal and informal networks. What's a network that actually makes the organization go compared to the one that they tell themselves about, to like looking at backwards work. I can give you some other references after, but like there's a few buzzwords, that's one. The other one's to get around the complexity of your fact you're actually looking at networks combined with interdependent on other networks. This classic interlocking directors. You look at who's on each other's boards or things like that, where you can then make where the assumption that there's some kind of actual unitary action going on is a little bit simpler because you're just going to see coordination of the board. And I was speaking to some people have that kind of data here. So that's a classic, well-trodden thing with lots of review papers and stuff that you can then go and dive down the rabbit hole and get into further. And I forget the book you sent me when I went to Jordan. If you ping me, I'll go find the title of it. It's a really nice sort of looking forward networks piece. Again, it's been a long time. Those are two of them. So computational organizational theory and the classic interlocking board of directors kind of those.
One of the things that I would focus on, just that the organizational point reminded me, is that the vast majority of our networks are constrained by our schedules, and managers create networks all the time. And so if you have the opportunity as, you know, a hospital manager to figure out when your nurses are scheduled, you're creating co-contamination networks of nurses and patients by virtue of the shift schedule. And when you start juggling people's shifts, you're creating random ties across networks, and you're increasing the extent to which the hospital is integrated from a, you know, transmission standpoint. That may or may not be good from a worker standpoint, but you can imagine saying, you know, I'm going to have people that only work particular shifts and segmenting that network and creating the opportunity. We built a model, which was ignored, and we can debate whether this is useful or not, for campuses that said you don't have to close campuses down. You can take majors, and you can if you just cut out the inter-major ties and you make students just focus on their core requirements within majors and cut out the general requirements, you cut 90% of the cross-student contamination risk for something like COVID, and you create little mini universities. And that's not as good, right, from an educational standpoint. You want physicists to take English classes, but for a year, it's better than staying home and being Zoom, right? And so you can imagine these kinds of trade-offs. You might imagine I had a dog in the fight and I lost. So, but you know, in retrospect, it might have been better from a learning loss trade versus contamination trade-off to let students have, you know, colleges within universities as opposed to just staying home and doing nothing, right? And I think that that's the kind of, when you think about what we do when we put people together, we create networks all the time. And organizational networks, you know, managers are network generators. They're just usually naive, unthinking network generators. And it's useful to maybe think about what that projection looks like. Tom?
I was going to say one thing real quickly. There's probably a whole lot of network analysis and very sophisticated network analysis that we don't know that the military is doing. I suspect they do more of this than anybody, and probably more of it than all of us combined.
Yeah, I've seen mapping of the Al-Qaeda network is like really good.
I'm sorry?
I've seen mapping of the Al-Qaeda network.
Yeah.
Really good.
The other buzzword you're going to bring out, high reliability organizations and design systems. So that's the military folks, they're a high reliability organization, and to achieve that, it has to actually be very particular structure, that sets sort of parameters of what you can do, and then the design systems literature is like, yeah, I would like this too, so can I get that? There's two other, I work in that space a lot, so those are sort of two other buzzwords where we want to go down that.
Please.
This is something I've been thinking about all week. So I look at like human service provider networks and organizational networks and human services. And I'm kind of, maybe this is a question is it just can't be perfect research, but if we like map a network and you can very clearly identify what is missing, like to increase the robustness, like this tie is missing, or this is where the bottleneck is. And it's very practical, like in this city, in this network, this intervention will be huge. How do you deal with that? Without reaching confidentiality, in an ethical way, or you make an intervention on a specific network you study?
Tom might have an answer to this. My guess would be that if it's something like a service provider networks, that there's nobody in that service provider network who would be unhappy that you helped them close a gap that's there. And so it's one thing to say what I'm going to do is help a city provide services for people that everyone in the city wants to do anyway, and they just can't see for their own, constraints of their own resources and whatever. So would you breach confidentiality? Maybe. Would anybody care? Probably not. And so I think that would, so it's going to be very case to case. But this is a problem that happens in many settings. That is literally the task of the consultant. You go into an organization, and that's exactly what they want you to do, is to find this problem, to solve that problem. So, Tom?
Just to add to that, my experience, just remembering things, right? So one thing in the project what we're trying to figure out is what physical spaces might be high risk for asteroid forming partnerships with data transmission. There's a thing, granted the data, we're using from a few years ago that sometimes there's a lag between when you collect data and what you find. So sometimes the landscape that you eventually find that pinpoint stuff about it's changed, right? And so there might be some less risk in that. But as far as reporting, I would say remember our approach one is when we're discussing, if we were to find that certain type certain spaces, if you're communicating that results academically, speak about it in as general terms as possible. Don't say it's like this place or that's the hot spot. You say it's like this kind of place, right? But because that specificity does matter as far as interventions, right? Increasingly there are demands for when you're working with vulnerable populations, like community advisory boards, and there's a way that maybe your publication speaking, generally, but as far as folks who really do it, perhaps you don't trust a government agency with some sort of sensitive information about where activity is happening. But if you run the community advisory board, you can get that. You can relay the needs for information to them.
And it might also be, in many of these cases, it's kind of, we were asked a question in a recent review about, what are we giving back to the communities we're collecting data from? And so one of the things we're giving back to the communities we're collecting data from is to help them see what couldn't otherwise be seen. And so I think in many times we're asking people to share information with us so that we can get a sense of the landscape. It's kind of our obligation to tell them what they're what it looks like. And they may or may not be able to figure out what the pieces are, and if there's something that's embarrassing, we should do our best not to do that. But if it can help the people who are doing this work a little bit better, I think the more of that we can do, probably the better.
I think that's becoming the standard in health research, is to be genuinely community engaged and be partnering with your community. And giving them back the data that you're taking from them, basically. Otherwise, they don't want to.
Right. Just a win-win.
Yeah.
Other questions, thoughts? What do you wish we'd done about? Go ahead first.
And also, networks doesn't have to also be deficit-based. Networks are strength.
Yeah.
So if maybe if you can uncover and you should uncover features of the networks that are strength for that population.
That's a great point. Absolutely.
Actually, I have the same issue we were talking about this night, but because I work with a lot of technology people who do critical theory evaluation on data, and I also they don't use so much process, which seems like a huge problem because a lot of our questions are network questions, right? But I wonder if there's
Yeah, there is there are a growing, I think the history of this has been one of hand-wringing and problem solving. And it's shifting towards, like, how do we solve the problem of deficits here, there, and there? Whereas I think it's shifting now to what are the disparities in these sets, and how do we balance them from one side to the next? I think there's been a language shift from deficits to disparities, and there's been a language shift from that's a problem to, like, how do we provide resources and capitalize on resources that are there. And so Michelle White, who's a pediatrician in our medical school here, has done great work in sort of in neighborhoods in Durham. And she has this great story, which I'm going to steal from her, which is she said she works on obesity and other sort of health, dietary health issues, and she put a map up at a community organization, and this woman in the back goes, "I'm effing tired of being mapped." Right? And it's like, I don't want to see another map that shows where the high obesity rates are in Durham, right? Instead, they tell me what to do about it. And I think that kind of a shift is useful. And so from our standpoint, we want to know what the big picture is, 30,000 feet, get all the landscape elements. But the people who live there, like, they know that people are unhealthy. They want to find a way to do something good with it. So I think it is useful to be sensitive to that. I'm not sure who's there, please.
I wonder if there's an opportunity there to like embed network findings then into like an evaluation methodology or framework where like you are evaluating both of those concurrent things and you weight them equally and like you are framing things of like what people are doing well and opportunities for growth. And so maybe that might be a space to like draw from traditional evaluation framework and that as a way to discuss and interpret what you're finding.
Please.
Is there any language that kind of goes outside of the qualitative sphere within networks regarding positionality, or like what's kind of coming out of the constructivist grounded theory related to, say, for instance, you're creating your network not through panels but through interviews and reflexivity and all this stuff in social networks?
There's certainly discussions. I mean, people use the tradition in network analysis is to use ethnographic terminology for quantitative, to describe quantitative patterns and such. So we talk about roles and obligations and these types of things. But I don't know if there's so much coming out of, so is that the sort of thing you have in mind, or?
Well, like for instance, I'm interested in studying Arab immigrants, and so I will be conducting interviews, for instance, and obviously, well, I'm not Arab identifying, so the potential, especially those who will be communicating with me in English, is who they nominate, potentially is impacted by who I am as an interviewer.
Right.
So I was just wondering if there's any language kind of, I mean, obviously like RDS could potentially help, or as we discussed, like targeted sampling and memory, but is there kind of more in terms of like?
Yeah, that's a great question. I don't have an answer for you. If some folks who have done sort of cross-linguistic data collection should chime in here, but my guess is that you're just going to that this is going to be a case where the initial testing and formative research, where you ask people and you say, all right, now that you told me this is what I'm taking from it, and do your best to work with a few close confidence that you can, before you actually go out and do the full field, to make sure that you're getting the answer out of it that they think you should be getting. And so that kind of back and forth is probably, that's what you do in any standard survey, but it's kind of a good thing. Tom?
Following up on that, it's one of the things like less linguistic, but it's touching on something Ashton said, right? Also, like as you're, I'm thinking about networks and data collection, but making sure that the categories, the things you're asking are relevant to the population. Like I met somebody at Sunbelt last year who studies like informal peer networks in like indigenous communities, right? And one issue he ended up having was that the networks that he was collecting was so dense because
All right, please, last thread.
It's not a follow-up question, it's a completely separate question discussing interventions and network interventions. Has there been research on like averaging of time of when to have the second wave of panels to analyze? Say if it's only like just you and assembly, like 1 week or 1 day program of when the second wave should be hit on, as networks had enough chance to change in that time? Because especially like as a student, you're given a certain amount of time you can create. So a lot of these options of temporal components are kind of limited because you're not given 10 years.
Yeah, it's the beginning of the seminar Monday morning, and then it ends, Friday afternoon, and so you've got a week, and then you may do a 2 or 3 week or 1 month follow-up, and that's about it. Generally, the work we've been doing in the field, there's been, the interventions usually take 3 to 6 months, and so you typically have a baseline, and then an immediate follow-up, and then either a 6-month or 1 year follow-up after that. Sure.
All right, folks, it's been a very long week. We have some people to really thank. Again, I just want to say thank you very much to the RAs. So in the back here, we're you've seen a lot of me this week, but I wouldn't be able to do any of this without having them in the back to do this. So it's a process that we just couldn't do, and they've done it for a few years now, and I think that they both love it, hate it, fear it, and dread it at the same time every year. And so there's a big sigh of relief that happened at Durham at about 2:30 on Friday of this week, and it's coming from this group, and so it really couldn't be done without them. We're really, really thankful to IID and Kathy Peterson. What's that?
Yes, Stockholm syndrome.
I'm working on that. We did. I encourage Stockholm syndrome. Very strong thanks to Kathy Peterson and IID. We are guests in their space, and they've been more than generous to us, and so we really appreciate their help. And to, I don't know if Bernie's here anymore, but again, if you haven't had a chance, our big thank you goes to NICHD. They fund this process. This is our second round of funding. We're going to we have a third round that's going to be coming here soon, and so we want to make sure that we're up and well to them. So if you haven't had a chance to do the evaluations, please go onto the Slack, find that link, do the evaluations so that we can have those to go. If you absolutely despised this workshop and thought it was a waste of your time and money, I apologize. Let us know. If you loved it, we're never opposed to hearing notes from people so that we can include those in our reports and show them to folks. So don't be shy letting us know how we did. So again, thank you all very much, and hopefully we'll see you all again soon.
I need to go because I have a flight in afternoon, but thank you so much and
Absolutely.
also for the team for putting this together, and it's such a great community and I learned so much.
Oh, good. I'm so glad. Thank you for being part of it.
Yeah, absolutely.
Will, have you had did you get all the slides you needed, Will?